Recording in progress.
Hello guys, good morning. Can you hear me?
Yes. Good morning, sir. Yes.
Okay, before moving forward with today's lecture, I'm going to tell that in the 11th of 18th of April, so the group presentation is going to start. And tomorrow, I think we have created a WhatsApp group as well. Tomorrow, I will, you know, send you the paper that you are going to present and the group number as well, right? So I think there are already 47 students, and yeah, so I will number the no okay, the groups are numbered, and I'll randomly choose a group that should do the group presentation on the 18th of April, right? So at the um end of the session, kind of 30 minutes, we are going to do that. Then 5 minutes for each student. It's already 25 minutes. Then 5 minutes on answer side. So any uh problem you have? Hello. Can you hear me?
Yes, sir.
Yeah, okay. I think you all are good, right? Can you see my screen?
Yes, sir.
Okay. Okay. So yeah. So actually, today we are going to deep um into one of the most and critical and kind of fascinating areas in the modern computing. So how we actually store the big data at scale and the philosophy behind the database system that make possible, right? Um, yeah, before we begin to let me set the scene, right? So actually, let's have a kind of a quick you know work through what we did last week, right? And we covered the core areas, what big data actually was and why it was hard and how we deal with it and what it mattered, kind of things, right? So we began by defining the big data infrastructure. It's not a kind of a single tool or system, but as an integrated set of distributed system, storage frameworks and computational platforms that work together to kind of, ingest, process, store, and, manage data at a kind of a massive scale. So then the other thing is we define kind of, five core functions, data ingestions. We cover the capturing data simultaneously from many different, so APIs, mobile apps, IoT sensors, log files, social media feeds, kind of stuff, right? Then we talk about distributed storage. We address why a single machine was insufficient at a petabyte scale, requiring data be is spread across clusters, kind of stuff. So then we talk about data processing. It was about, turning stored data into something like, useful true batch jobs, real-time stream, then interactive queries, kind of stuff. So we discuss about resource management and explain how tools like Yarn, Yet Resource Negotiator, and the Kubernetes, which jobs received, and kind of CPU memory and data across hundreds and thousands of machines. And last, we discussed about, fault tolerance and the scalability that highlighted what separated in big data infrastructure from the traditional system, the ability of keep running when machine failed, and to scale horizontally by adding machines rather than replacing them, right? So then we talk about 5 P's of big data. We explore the 5E model, the most widely used framework for describing what the main data big. And first one is we talk about volume, and it's refer kind of terabytes, petabytes, and beyond, right? So we noted that kind of a kind of Facebook stored over kind of 300 petabytes of data that the then kind of we talk about volume was what forced us into kind of distributed systems. So then we move on with the velocity. The other we it was about the speed at which data was generated and that need to be processed. So we got example on the stock exchange that handle millions of trades per second, kind of tweet examples, how many tweets that tweet kind of every second, kind of 6,000, I think. So we established that um, kind of fraud detection system, how to capture in fraud transaction, So kind of things that we have identified that velocity was what demand streaming processing infrastructure as well. So this is a kind of a quick recap of the last lecture. So okay, then the other one is volume. We talk about velocity and variety, right? So we described the data um, formats, right? The diversity of data formats we covered is structured data such as database tables, semi-structured data, kind of XML, JSONs, then unstructured data, kind of audio, video, stuff like that, and uh, we talk about that it's kind of 80% of the world data was unstructured, right? So the the traditional data relations databases were not built for that one. So then the other factor is kind of veracity. So veracity is kind of address data quality, and we discuss how you know the the social media data could be kind of reliably false, and we say talk about at a petabyte scale, the poor quality data, it lead to very expensive and wrong decisions, right? So we talk about which was why the data quality frameworks and data validation pipelines were necessary. So then finally we talk about the value, the last V. So it was described kind of important of the dimension of all the volume, velocity, and variety in the world mean nothing if the insights could be extracted, right? So we frame that the three V's and define what we made it hard, and while you know variety and value remind us why it mattered. So then we talk about why big data is hard, and we work through the four kind of hard problems that make kind of big data is challenging, right? So for example, we talk about storage, right? So we work through the numbers and kind of storing 1 petabyte roughly required 1 terabyte is kind of stuff, and the what tier we talk about the tiers, school tiers, and we discuss how we choose the right storage tier, and it was a kind of a real engineering decision, so that to significant budget consequences, right? So then we talk about the other kind of hard is kind of moving data, right? So even on a kind of a, let's kind of say that the 10 GB network, so copying 1 petabyte would have taken kind of lot more days to continuous fast, right? So the kind of stuff, and we talk about that the moving computation to the data, not the data to the computation, right? The principle that fundamentally shape how the big data architectures were designed. So then other thing is actually we talk about the processing stuff. We calculate kinds of how many for example, I think we talk about the 1 petabyte on a single machine at 10,000 records per second with a 1 kilobyte per record. That means kind of we have taken processing around kind of lot more CPUs, right? The for that kind of solution stuff, the solution was kind of distributed processing, the partitioning across data with many machines and processing parallels. Kind of with 1,000 machine, we can figure it out kind of a lot more easily than the processing in a single machine, right? So we talk about the map produce, right? So and how the Spark that why those built to do, right? And finally, challenge, we talk about the data complexity. We discuss how the thousand of contributing introduced to the kind of uh, kind of um, the data complexity at the kind of how machine failed, and we talk about some even a single day the machine can be failed, and the network latency and the partition were unavoidable. So we talk about the fault tolerance had to be first class concern in a kind of a system design. So then in that lecture we talk about ETL and ELT as well. ETL means extract, transform, load, and so ELT means extract, load, transfer, right? So in kind of it was a kind of a traditional approach ETL, and the data was extracted from the source system, then transfer on a dedicated processing server, then we join it or aggregate it or we clean it up and then load it as a kind of a clean result into a data warehouse. Okay, so we talk about the in the ETL processing, the transversion happen before the data entered to the target, and for the ELT thing, it was a kind of raw data was extracted after loaded directly into the target system first, right? Then transform what happened, in the inside the kind of, it can be have its own processing power, right? So we explain why the ELT have become okay. So we talk about the ELT, so how it become more popular in the cloud platforms like Snowflake, Databricks, and stuff, right? So then crucially how the raw data were preserved and how cloud always to be reformed differently when the requirement changes, right? So and we notice that the actually the modern big data system use ELT, right? So that's what we did actually, and we discussed about the big data system architecture overview, right? So we talk about the data sources, kind of data sources layer, actually the layers of the system, right? Data APIs, IoT sensors, then the accession layer, Apache Kafka, how Kafka having become kind of a standard for the real-time ingestion, and we talk about the storage layer, the HDFS, then S3 NoSQL database that we are going to talk about today, and kind of next the layer is processing layer, the Spark, Flink, MapReduce performing, on the analysis, the final layer is kind of presenting layer kind of stuff, right? So then we talk about the batch processing, stream processing kind of stuff, and yeah, in the future lectures we are going to kind of deeply talk about this kind of processing stuff, right? So that's the deal for the last lecture, and I give you kind of a quick recap of the last lecture, right? So today actually we are going to talk about the you know um talk about the fundamental difference between SQL and NoSQL databases, and why distributed system require us to make different kind of compromises things, and how to choose the right database technology for a given problem, and these skills that you will apply through the actually when you're at the industry, it will help you to apply kind of stuff, then so okay, so in next week actually I'm going to do a kind of a practical thing related about the MongoDB, using MongoDB, a document type DB, and yeah, that's what I'm going to do. So yeah, let's move with the lecture. Okay, so this is the lecture overview, right? Okay. So yeah, let's take a kind of a moment to look the roadmap today, right? So we have kind of a rich agenda today, but I want you to know we are before we are starting, we are heading before, right? So we begin with the fundamentals of the data and analytics. So sometimes these factors, but I am going to uh, do it. So then especially data life cycle, what analytics really means, and four types of discovery that analytics available, right? So this is the why behind all our infrastructure choices, right? So we store data because we want to extract knowledge from it, right? So that's a kind of a good important factor. So why our infrastructure choices. So then we move with the traditional analytics, the five types from the descriptive all the way up to decisive. Then you know understanding this ladder, because it's a kind of a ladder stuff, right? So moving from traditional analytics, right? So that means then we need to understand this kind of a ladder. It's because it's directly inform how the your database needs to be performed, right? So then a system design for descriptive reporting also very important performance characteristic. So we are going to talk about the real-time predictive kind of stuff as well. So after that, we are going to cover the SQL databases and ACID properties. Even if you know SQL, I want to think about the kind of a different kind of stuffs and how we guarantees that the powerful and kind of we are talking about the traditional transition into kind of big data and challenges and in the traditional system. So we are spending before we spending on time of kind of NoSQL database, we need to know uh, what are the what are they and how they work and kind of different types and cap theorem based um, kind of stuff and all of his stuff, right? So yeah, so that's the lecture overview for today. And actually, as I said you earlier, it's a kind of a rich agenda, right? Okay. So, okay, let's talk about the data life cycle, right? Okay. So, before we talk about the databases and storage, I want to, you know, tell why the data exists and what journey it takes from the creations to usefulness, right? This is called data life cycle. Okay, it has 5 stages: log data, acquisition, aggression, analytics, and application, right? So stage one is kind of log data. So this is how data kind of a primitive form, right? So think of kind of at the server logs, the sensor readings from IoT, when you click a event from the mobile app, kind of a financial transaction kind of stuff, right? So at this point, the data is scattered, then kind of unprocessed and typically stored as a flat file, so kind of a stream, right? So it has a potential value, but not yet released, okay? Um, okay. The stage two is kind of acquisition stage. So this is where we collect and scatter data and bring into the system tools like Apache Kafka, right? We talk about that one. And there are some cloud ingestion services as well, kind of Azure service bus stuff, right? So the goal is to capture everything without losing events, right? Even under high load as well. So the third one is called aggregation, right? Aggregation. Aggregation means rollouts from thousands of servers or kind of millions of users need to be cleaned, then deduplicated, then kind of transform and combine into kind of stuff. This is kind of a ETL stuff, right? So we talk about that and we talk about this stage and we talk about how the data engineering becomes critical. Okay, so the fourth one is analysis. Okay, so this is where the data produce insights. You know, tools like Apache Spark, Hive, even machine learning frameworks, right? We run computations over the aggregated data to find the patterns, build models and answer question kind of stuff. Okay. So the stage 5, the last stage is called application, right? You know that, you all know that one. No? So the knowledge extracted from the analyze, we put it to use. Okay, so it can be kind of a recommendation engine or kind of a, dashboard editing that can be happen, right? So that's the thing actually. The URI architectural decision we discussed today, the which database to use, how to model data, kind of whether to prioritize of the consistency or availability. So we need, these kind of concepts to know, because this life cycle is efficiently at the scale. Okay, that's what I put this slide to discuss kind of a quick recap about the data life cycle. And yeah, okay, this is the analytics equal discovery, right? What does that mean? Okay, so I need to think about this kind of stuff carefully. So most people think that analytics mean, building reports and dashboard, right? Kind of, counting things like, revenue stuff. Or yes, that's a kind of a simple kind of analytics, right? But true analytics is about discovery. So it's about finding things that nobody knew existed before, right? So that's why we are going to do some kind of analytics. Okay, so there's a kind of a data scientist. There was a data scientist known, I think, Kirk Bone, who introduced kind of 4 types of discovery, right? So novelty discovery, uh, class discovery, association discovery, and the correlation discovery. Okay, so and so first thing is so this is a kind of a slice in one SAL. In the next slide, I will lead them into kind of the novelty discovery and stuff, right? So okay, so first is novelty discovery. So for finding rare or one in a millions of year, right? So this is a kind of a something unusual can happen in your data, but never happened before. Okay, so your job is to catch it, right? So for example, the I talk about the fraud detection system. So if you talk about the fraud detection system at the visa process, kind of, let's say, how many transactions? About 150 million transactions. So, if we take the fraud rate is roughly 0.1, the 0.1 from the 150 millions is kind of how many? 150,000 or something like that, right? So the system must find those 160 fraud transaction in 50 millions of legitimated ones. And so that's the novelty discovery in production. Okay. So the other factor is kind of class discovery, right? Class discovery means identify new groups or categories that did not previously have neighbors. Okay, you know, you don't know how to advance how many groups that time or what they look like. The data will tell you. Okay, so for example, if we talk about kind of YouTube or Spotify kind of stuff, so it did not start with the predefined music genres that their user for their recommendation engines. Okay, so they clustering kind of they run kind of clustering algorithms on listening behaviors of the data, and discover natural grouping that they label, so genres like hip hop or something like that. So they used to use their users pattern at the very first of the start day of that user. The Spotify, they cannot predefine. So with the use of you know data, and the how the users are like to hear the music, they normally clustering algorithms on that data, then label it. Okay, that's a kind of a thing that the class discovery does. Then third one is kind of association discovery, right? So for example, finding things that unexpectedly occur together. Okay, so there's a good example actually in 1990. I don't know whether you heard about this one. The in 1990s, in a kind of a um, shopping complex or kind of stuff, they found that the beer and diapers were frequently bought together on the Friday evening, right? So the association was not predicted, but it was discussed. Okay, so when you talk about the in Friday evenings, so the beer and diapers were frequently brought together. So it cannot be, the association was not predicted, no, but it was discovered, right? It was a kind of a um, kind of a interesting case study in 1990s. So what happened is, uh, you know, a kind of a retail store, I think a Walmart or something like that. They find that the people who buy diapers oftenly buy beer. Okay, so this is a kind of a surprising thing, and they are completely unrelated products now. So normally you wouldn't expect them to bought it together, right? So the real reason behind that one is the main buyers were young fathers. Okay, they used to go buy diapers and in the on the Friday, and while shopping they are picking up beers, right? So the connection is not between the products. Actually, it's about the customer behavior, right? So this type of analytics, actually we talk about market basket analysis, right? That means the find the products that are frequently bought together. Okay, so he uses technique like association rules, kind of a priori algorithms or kind of stuff. He used that one. So that's a kind of a good example for the association discovery. Okay. So then the fourth one is kind of correlation discovery. So finding mathematical relationship between the variables that may reveal deep truths. So this is how this scientists discover correlation between kind of like smoking and cancer, air quality and asthma kind of is, and the social media use and the sleep quality. That kind of stuff is under the correlation discovery. Okay, okay. So why does this matter for infrastructure? We need to think about that now, right? So because of each of discovery type has a different computational and storage requirements. Okay. For example, novelty detection, right? It means real-time stream processing. Okay. Then class discovery, it needs kind of clustering algorithms and huge data sets, right? Then association discovery needs kind of transaction data across multi millions of records and kind of stuff. So each demands a different parts of our big data stack, right? So these are the kind of deep dive into novelty discovery and stuff. So I think let's walk through these concepts as well, right? So it's I know it's a kind of a boring stuff, but it's good to know this kind of basic type of concepts, right? So so this is the first two analytical discovery, and the novelty discovery and the class discovery, right? So because of understanding then concretely, it help you to why big data infrastructure need a kind of so powerful, right? So again, I would like to say novelty discovery, it's a kind of art of finding a needle in the haystack, right? So what makes an event in the novel, it that be you know diverts significantly from the established patterns, right? It's a rare one, it's extreme, and often it's most valuable signal in your entire data set, right? So I found a good example for a novelty discovery, a patient in a kind of a heart rate. Okay, so I mean patient in a kind of a ICU. So in healthcare, kind of hospital monitoring system. It processes thousands of patient readings per minute, right? So a kind of patient heart rate, blood pressure, oxygen, saturation, kind of stuff, right? But a machine model training on a millions of historical records, right? It might be detect a kind of a subtle pattern and kind of a this if it detects a kind of a subtle pattern, so then this novelty discovery is very important because it's a saving a life, right? So in this case actually we need to think about the data imbalancing, right? So the what makes novelty detection technology hard is kind of class imbalance problem. Okay, so when even if a fraud is kind of 0.01 of transaction, and if your model say it's not fraud for the single transaction and it's 99.99 kind of a accurate one, it's completely useless, right? So building system that can find genuine novelty requires careful algorithm, high performance designing, good defining, you know even infrastructure to process data fast enough to be actionable. Okay, so that's why novelty detection is kind of technically hide behind the imbalance problem. So the next one is kind of class discovery. It's a kind of a different one. If you think about the natural grouping in data that were not predefined, right? So, for example, you do not, you know, come with the data with the category in mind, right? So you let data to self-organize and then you interpret what group to mean, okay? And from the infrastructure perspective, the class discovery typically requires a kind of iterative processing of large data sets, right? Because we are running clustering algorithms in a multiple times with the different parameters, right? So then we storing immediate results and comparing outcomes, right? This is a kind of a classical kind of batch processing workload, and we need tools like Hadoop, MicroVideos, Apache Spark kind of stuff. So the next slide is related to the other two discovery, association discovery and the correlation discovery, right? So association discovery is kind of finding items, um, you know kind of what finding items or events that co-occur more than a chance would be predicted, right? So, for example, if I tell you that people who buy tennis racket also buy tennis balls, that's obvious, no? But if I tell you that people who buy kind of sugar kind of stuff at 8 p.m. on a Sunday, it's a kind of a more signet frequently, like to buy vanilla essence, baking powder, or kind of stuff, right? So this is a kind of a association that worth acting on. Okay, a supermarket can use that knowledge to redesign their layouts. For example, if somebody buy sugar, then the supermarket can redesign their layout to put kind of vanilla essence and baking powder near to it, right? So this kind of association discoveries can use that knowledge to redesign their layout, create a target promotions, and kind of stuff, right? So the infrastructure is challenging here is computation is scale because the association rule is a mining algorithm, like the a priori algorithms, right? So then this requires distributed computing across many machines, not the single server would take days to um, weeks to process, right? So the final discovery is the correlation discovery, right? So correlation discovery is finding the mathematical relation between continuous variable, right? So unlike association one, it deals with discrete events, right? The correlation work with quantities, okay? So for example, this temperature, go up as altitude goes up, kind of stuff, right? So this relation may be linear, but it may be kind of complex, non-linear function that only machine learning can be detected, right? So yeah, those are the things that we need to talk about the discovery. And again, I will tell you that the why does this matter for infrastructure, right? So because of these kind of discovery types, it needs kind of different types of computational storage requirements. So we talk about novelty, it needs kind of real-time processing. We talk about the class one, need kind of clustering algorithms. So we talk about associated discovery. That means, transaction data across millions of record, the distributed computing of stuff, and we talk about the correlation discovery as well, the kind of the huge machine learning algorithms need to be run. So the next one is kind of, we are going to talk about the challenges, right? So challenge of the data analytics. Okay, so the first challenge is pattern detection, right? So, okay. So, and let's move to the what the analytics can discover and how hard it to relate reality what makes analytics difficult, right? So, to be honest, it's the analytics at scale is genuinely hard. Okay, so it's not just a kind of a matter running on a big query on a big machine, right? So these fundamental challenges are new thinking, right? So the first and the most fundamental challenge is kind of pattern detection, right? So finding meaningful signals inside the massive noise. Okay, so this sound straightforward, but it's a kind of a extraordinary complex at a scale, right? So, you know, for example, it's take kind of a data volumes that we are dealing with, right? So the Google generates 4 petabytes kind of data new daily, right? Twitter process 6,000 tweets per second kind of stuff, right? Then in that case, the torrent of data, the patterns that matter, right? So, kind of the early warning sign of a trending crisis kind of stuff, and, imagine forwarding kind of customer behavior. They are kind of a tiny ones. Okay. So there are two types of distinct types of pattern that may make this challenge, right? So first one is a kind of a single event run. So one transaction, one sensor reading, kind of one use action for its own signal, something important, right? So uh, let's kind of a a single SQL injection that attempt on a web server. So kind of stuff. These sometimes can be caught in a simple threshold based on rules because it's a kind of a single event, right? So the second type is kind of harder. It's sequence of events, right? The pattern only reveals itself when you look at the series of action that in a correct order within a specific time window, right? For example, let's say that consider about the fraud attack, right? So attacker first checks the account balance, then kind of changes the email address or kind of request password reset kind of stuff. It's all within 4 minutes, right? So it's not a kind of a single action in fraud, only the sequences, right? So for example, we are dealing with the sliding window. Okay, I think you heard about the sliding window technique, right? So sliding window means, so for example, let's say that the bank fraud detection, it's a kind of a simple explanation. Okay, what happened is let's think that the bank processes 35 million kind of transaction per day. So it tries to detect fraud patterns, right? So it what it will do, it looks at the recent transaction kind of last 72 hours for each account. Okay, so the concept behind this one is kind of sliding window concept. The sliding window means, always looking at the most recent time period and move forward as new data comes, right? For example, let's say that we have 72 hour sliding window, and in kind of 10 a.m. system clock. So we look at the last 3 days kind of data, right? So then at 10:05 a.m. so window moves forward and then drops all data and new data, right? So the window is always sliding in a forwarding time. That's a kind of a sliding window. Okay, so it's a kind of a deep concept, right? So I told you because the industry kind of stuff, it's using this kind of technique, right? So um, that's a kind of a second type, why the sequence events are much harder, right? So then we are moving into pattern understanding, right? Give me a minute. Okay, so we are going to talk about the pattern understanding. And finding pattern also kind of a battle stuff, right? So kind of the second challenge is kind of perhaps harder than what is understanding pattern actually meaning. Okay. So when your machine learning algorithm models flag you, it's a transaction or kind of stuff as a fraud. So it's because some combination of features, right? So for example, let's say some combination of features like the merchant category, transaction amount, time of the day, geographic distance from the previous transaction, the device fingerprints, and kind of those are produced kind of a high annual score, right? But we need to see which combination and why does combination matter, and does this always mean a fraud or in only a certain context, right? So for example, I'll tell you kind of example, right? So there's a company's risk team, and one discovers they had the fraud detection modulos flagging a uh, kind of a fraud detection transaction at an unusual rate. Okay, so for a specific merchant category, right? So their model detects or flagging kind of a transaction at an unusual rate for a merchant category, right? So that merchant category, as it was a kind of a pet supply store. Okay, so they um find they in that time they usually found that was there any kind of a fraud operating to the pest stores, right? So after investigation, they discussed that the model had to learn association with that merchant category with a um, kind of a demographic group. Okay, so this model was technically correct, but misleading because the merchant category is kind of a pet supply store, right? So that's why I'm telling that the we need to think about which combination and why this combination matter, and why does it always mean a fraud or kind of a certain context, right? The pattern understanding. So the code challenge is a kind of a consent. So some pattern can be mean completely different things depending on what occurs, kind of who involved, who proceeded that, right? So, for example, kind of combination increasing with the heart rate reduce the sleep quality or more frequent on the Google searches, kind of flu stuff, right? So this kind of stuff, it's might be kind of same pattern but completely different means, right? So that's why the domain expertise, um, much more remain in the essential of data science, and the algorithm find the pattern, and kind of the doctor or kind of a fraud investigator, business analytics. It's they need to be kind of expertise at pattern understanding, whether it's meaningful. Okay. So for the data infrastructure, that the challenges means we cannot just build system that produce outputs. We need to build the system that produce explanation. Okay, so the modern kind of AI framework kind of stuff, because they are exist precisely because of this challenge, right? So that's the understanding of the pattern understanding. When we talk about the finding pattern not enough, you must correctly interpret what it means in context. Okay, so I explain it with the kind of examples as well. So you can read this, right? So then the third one is kind of challenge is prediction, right? So actually, yeah, it's a prediction is a kind of a challenge in the data analytics, and moving from understanding what has to happen to forecasting what will happen, right? So this is where analytics become most economically valuable and more technically demand, right? So the fundamental idea of the prediction is that the past contain actually signal about the future, right? So for example, if customer who show pattern kind of a let's say extend or something like that, so who cancel subscription within 30 days, then new is customer who start to showing the behavior pattern also at a risk, right? That means if customer shows who shows kind of a behavior pattern that if they are going to cancel their subscription within 30 days with the user patterns, then we can detect that there is a risk if new customer also starting shows the be showing the same behavior pattern, right? So that's the kind of a stuff. So what make prediction technically hard is that in the future it's not in the past, right? So that means the the models are trained on the historical data, right? So they are applied to a present that is constantly staging. Okay, so this is the data drift problem, right? So the consumer preference changes, kind of the market involved, the new products are launched, kind of stuff. There's a data drift, right? So models are trained on historical data, right? So for example, the events like pandemics and regulation challenges, kind of stuff, they are there's a data diff, right? So for example, in 2020, the every demand forecasting model in the world, right? Kind of the large companies like Walmart, Tesco, something like that. So it was trained on the years of historical purchasing data, right? Within 2 weeks of COVID-19, the lockdown announcements, the consumer behavior changed so dramatically, so that the mall trained on the previous 3 years of data become almost worthless, right? Because in that time there's not kind of a experience in the pandemic. So model also trained on the historical data where that the model pandemic stuff are not in there, right? So for example, the kind of the model has to be retrained almost with the weekly, because in that the 2020 remember that there's a pandemic situation, and the kind of data drift almost there, right? So from the infrastructure perspective, so the prediction requires ability to run models, right? So at a scale in a real time, right? So the batch prediction model might be accepted for churn prediction, and we need to run it overnight, right? So kind of stuff. So the demand is not just a kind of a good algorithm, but fast databases, low latency, and kind of careful feature of storage architecture, right? So mm, yeah. So the next challenge is data complexity. Okay, the modern data is heterogeneous and it comes from many sources and many formatters simultaneously, right? So you know that the real data is messy, right? It's heterogeneous. So it comes from different kind of formats, right? So um okay. So if we go to kind of a example, so kind of um uh, good example, okay. Okay, when kind of a banking example, right? So they discovers that over kind of 3 million duplicate customer records are across their two system, right? The deduplication project just identify which okay. So it took 18 months to recover developing a custom matching algorithm that compare names kind of matching address with the kind of a fuzzy logic, right? That's why the data is big complexity. So for database system, this is kind of a log file from the server. It contain unstructured text, and the mobile apps also even arise as a JSON. Then the financial transaction come as a kind of a the flat files, the IoT sensors. They produce binary time series, right? So the social media can produce mix of text, images, kind of stuff, right? So all these arrive simultaneously at a high velocity, and it need to be stored, processed, and analyzed together. Okay, this is actually precisely why the NoSQL database were invented, right? So the relational database with a kind of predefined schema actually struggle to accommodate this kind of heterogeneous resources involving data structures. Okay, so when you add a new attribute to customer profile, say that you want to start a recording kind of a new attribute in the SQL database, what you have to run is you have to run alter table migration, right? It will mail the log for the table for the hours, right? In the document DB like MongoDB, you can just simply include in the field in a new document. But the important factor is the existing document are not affected, right? So that's why the NoSQL database, it was invented, and we talk about the challenges of the data complexity, right? So then the last one is uncertainty, right? So uncertainty means I don't not mean that the uncertain about our infrastructure. I mean that the analytics, unlike traditional software development, we are working on the problems where we do not know right answer in advance, right? So in traditional software engineering, requirements are clear. So for example, build a login system, right? It either work or does not work, right? You can write test cases, right, that have defined kind of pass or fail outcomes, right? In data analytics, you are often exploring, right? You do not know what are you looking at until you find it, right? So there is no unit test kind of you know um, unit test kind of stuff, and there is no kind of integration test as well. There are two, I think you all know that one, right? So this is a kind of extra knowledge. There are two types of testing, right? The unit testing and integration testings. So in a kind of an interview, they used to ask that one, what's the difference between unit test and integration test, how you write it, kind of stuff, right? So there's no clearly unit test for the kind of analytics, because in the data analytics, you are often exploring and you do not know what are you looking at it until you find it. Okay, so the uncertain challenge also kind of manifest the model evaluation. So when you build a kind of a machine learning model for a kind of a prediction, you cannot know certain whether your model is correct. You can measure it by historical accuracy, right? So and approving the kind of, for example, let's say we build a machine on predicting kind of a kind of what approving loan, something like that. So based on the factors, we can the model can predict it where it needs to be approve the loan and rejecting the loan, right? That's kind of stuff. So for the infrastructure stuff, this means we need good system at upon experimentations, right? So A/B testing platforms kind of stuff. That means the feature stores allow you to repeat model iterations, the shadow modes that you let kind of stuff, the parallels processing. So this system makes analytics under certain uncertainty kind of tractable kind of scenarios, right? So actually we talk about these challenges, right? So the prediction pattern understanding and how the infrastructure uh, use these kind of challenges to improve our big data infrastructure, right? So the next section is kind of traditional data analytics, right? So yeah, so now we are moving into kind of another section. So before we deep dive into kind of stuff, we need to have a firm foundation where traditional analytics looks like and what are the limitations, right? So the word traditional means actually it's not obsolete, right? So that means if you think that traditional means it's obsolete, it's not, right? The descriptive analytics, the reports that do dashboard and summaries, right? It's still they are commonly used in analytics, right? For the most organizations today as well. So the difference between the big data and the advanced analytics is open as kind of the possibilities that were simply impossible before. Understand the progression help you to when to apply, which to apply, right? So we are going to talk about the five types of analytics and arrange in order, increasing value and increasing different kind of difficulty. Okay, so descriptive, diagnostic, predictive, prescriptive, and decisive. Okay, so first one is descriptive analytics. This is the kind of simplest and the most widely used analytics. You all know this thing, right? So it's purpose to kind of straightforward, right? So summarize, okay, what has already happened. Okay, so it answers the question what happened, right? You can see in here, descriptive analytics mean what happened, right? So how we can get the answer? So by aggregating kind of historical data into reports, dashboard, and visualizations, right? So think of a descriptive analytics is a kind of a, it's a kind of a review mirror of your organization, right? So it tells you how exactly you have been. For example, last month revenue, then kind of the quarter's customer acquisition numbers and the number of support tickets sold per today. So these are called descriptive metrics, right? So techniques for the descriptive analytics are kind of aggregation functions like some average, median, standard deviations, and we can use standard reporting tools like the Power BI, even Google Sheet also kind of a primary tool, right? So the data records are relatively modest, but well structured relational database within a few years also, historical data typically is sufficient, right? So there's a kind of a key limitation, and it does not explain or it's predicted, right? So for example, it only tells what happened, not why. Okay. So it backward looking and cannot explain the root cause, okay, and as well as the predicted future events as well. So because of this one, so for example, let's say that the sales last time the sales dropped kind of 40 or something like that last week, right? It will not tell you whether that was because of the kind of reason, right? Kind of a promotion and dinner kind of stuff, right? So for that thing, we need to move it to the other one, right? How and what, how did it happen, right? The diagnostic analytics, right? So this is also kind of an important analytics. So in the industry also, when there's a kind of a system failure, the the managing team asks from me how it what happened and how it happened, right? So there are some metrics, so I can see, okay, this time there's a crashing in the machine, so I need to find how it happened, right? So there are some diagnostic matrices as well in the kind of Azure stuff. There are some section called diagnosis analysis, right? So then in that, when we discover the matrices, you can see, okay, there's a kind of a issue in the machine in that time, kind of a peak load kind of heating, or the CPU and memory not sufficient, something like that. So there's a diagnostic matrix that tell you why it happened. Okay. So the diagnosis is kind of a, you know, it takes the uh, descriptive analytics, what cause, and ask why, right? So the key techniques are kind of, de-aggregating summary metrics, right, into their component parts and where it originated, right? So then the correlation analysis and finding which variable mode together, which with the kind of metric of interest, right? So this is the approach that yeah, user can use in the kind of technological companies as well, right? So actually the Google's, Netflix, so they are also kind of a post-mortem process. They are funded to use the diagnosis analysis. Okay, so looking at the logs, matrices, traces, events from the period of time and what changed, how did change, and what happened, something like that. Okay, so this is kind of a diagnostic analytics stuff, and the next one is what will happen, the predictive analytics, right? So it is where that analytics start to become, generally informative, right, transformative, right? So rather than telling you what happened and why, it tells you why likely happen next. Okay, so there's a shift from the hindsight to foresight, right? The predictive analytics uses kind of the statistical modeling and machine learning algorithm trains on kind of a historical data to forecast the future outcomes, right? So the fundamental assumption is that the pattern can be held in true, the past will continue, and that hold in future as well, right? So we have discussed the data drift, right? So we discussed that one. Okay, so so for example, let's say kind of insurance system. So if they use predictive analysis over kind of 200 years, kind of when you apply kind of life insurance, the company uses your age, then health, occupation, lifestyle, and kind of stuff, then they can probably predict you the time period, right? So it tells you kind of a valuable um, to the insurance companies, and so the predictive analytics is kind of literally foundation to the insurance industry as well, right? So in modern technologies, companies and the predictive analytics using churn prediction, right? So for example, which users like to cancel their subscription with 30 days, and then the demand in forecasting and how many units of each product should be stock for next kind of stuff, right? So the infrastructure requirements for the predictive analytics is substantially kind of higher than the descriptive and diagnostic, right? So you need historical trained data and run computational model training processes and store training models, then serve prediction at low latency kind of stuff, right? So this often requires to dedicated of store, feature storage and serving infrastructure separate from your operational databases, right? So that's why we are dealing with the kind of the the idea behind this one based on the each of predictive analyticals. So we need to see what causes the infrastructure, right? So what's the new initiative for the big data infrastructure stuff, right? So the next analytics is the prescriptive analytics, right? So the prescriptive analytics kind of one step further, right? So for example, the predictive analytics say, okay, here it will be happen, right? So the the prescriptive analysis say here what you should do about it, right? It move from forecast to recommendations. Okay, so it's that technique is kind of let's say the mathematical optimization, the linear program kind of stuff. So which allow you to test different decision scenarios before committing into one, right? So for example, in the healthcare industry, this is increasingly applying the prescriptive analysis, right? It's for the treatment planning. So for example, for a given patient diagnosis, so or for given kind of a patient genetic profile or treatment history, the prescriptive system can be recommend which combinations of treatment is mostly like to be effective. Okay, and you know it's the kind of a power of the analytics, right? So for the when you talk about the you know infrastructure challenge of the prescriptive analytics, the optimization problem can be computationally intractable at a scale, right? So the global optimum for kind of, for example, let's say the global optimum for the routing problem with 1,000 vehicle and 50,000 delivery stops are mathematically it impossibly solved. No? So in the real-time system, use appropriation of algorithms, then constraint programming, and the computation is good enough to find the solution quickly, right? So so this is the kind of the technical we talk about that one, and the example and the limitations. So it depends on heavily on model assumption. So and because it depends on the prediction, right? After predictions, we need to take recommendation, the prescriptive. So more, it depends heavily on the model exceptions, right? So what should be happen is if there is not a kind of a good enough quality of the results, then we are misleading, right? So the last analysis is decisive analytics. Okay, it's the you know that term described system is designed to support human to decision making, right? When presented with a set of alternative, right? So the key distinction is from the prescriptive analytics is that the human remain at the decision loop, right? This system present the option, context, probabilities kind of stuff, right? So uh, okay, so for example, for the kind of clinical decision support system in the hospital, so when doctor is kind of treating a patient with kind of stuff, right? Based on the patient's presentation, there are three mostly like diagnosis, right? Let's say ABC. So ABC has possible of kind of 60, 20, then 10%, right? So the recommended treatment path is always as kind of the the similar patient with the diagnosis A and this treatment to be has to be done because it has 70% of survival rate, right? This system informs and support. Okay, so that helps to doctors to decide which of the diagnosis pattern used to to be done for the patient, right? So but the technical thing is it's decisive analytics are they are primary in kind of visualization kind of stuff, right? So it's a kind of a complex, uncertain information is the one that human decision maker can be quickly understand, no? So this is why they introduced the kind of decisive analytics. And another example is kind of let's say that the treasury department. So for a treasury departments also they use a decisive analytics dashboard for the foreign exchange risk management, right? So then the system shows how the real time currency proportion and forecast rate and kind of stuff, right? So in a single view of this stuff, it can be seen the real time current position, the currency position and stuff. Okay, the treasury manager can immediately take this proposition and you know based on the available data, then the treasury manager can give the correct decision on that one, right? So then the important kind of dimension here is because you know AI system nowadays it's more capable, right? So it's moved to pressure to kind of move from decisive to perspective, right? So it automate more decision, right? So that's why they are not just kind of a technical question, but as you engineers, you have to grapple throughout this career stuff, right? So that's why we are using kind of the decisive analytics. Okay. Mm, okay. So this is the levels that we talk about: the descriptive, diagnostic, predictive, and prescriptive, right? So again, descriptive means what happened, diagnostic means why did it happen, predictive means why will it happen, what will happen, and prescriptive means how it happened, how can we make it happen, right? So then yeah. So it shows that so if we talk about this kind of a ladder stuff, okay, as you move from the descriptive to decisive, so two things change simultaneously, right? So it's the value of the delivery increases, then the difficulty also increases, right? So the descriptive analysis at the kind of a actually this is not the bottom, it's a lower layer, okay? So it provide a kind of hints type site, and it's relatively low because it tells you about the things that have already happened and cannot be changed, right? So but it also relatively easy to implement, and a well-designed data warehouse also or BI tool can be deliver excellent of descriptive analytics with a small team, right? It's informative and hint style. So other thing is diagnostic. So diagnostic means analytics, it adds data mining, correlation analytics, machine learning, and stuff. Okay. Then the predictive analytics also add machine learning, and prescriptive also add optimization, and decisive adds the human computer interaction, right? So actually, um, in our course, that this course actually for the big data infrastructure, the descriptive analytics that runs on a traditional data warehouse. Okay, the predictive analytics at a scale need to be distributed in a kind of a training infrastructure. So the real-time prescriptive analytics needs kind of streaming processing, low latency, and this is why we understand um, this kind of analytics maturity, right? And this is kind of another kind of infrastructure evaluation, the analytics landscape. Okay, so in early phases, it's a kind of a standalone um, databases, right? So in the financial had their own Oracle database, then the marketing had their spreadsheet kind of stuff, right? So each system capture data for their own purpose, right? There's no integration. Okay, so descriptive analytics was possible within this silo, right? So, but across the functional analytics required the manual data collection and the kind of the cross-functional analysis, it required kind of manual data collection, right? So this is in the early stages, right? So the integrated data, right? So it was kind of data warehouses, okay? The centralized repositories that aggregated data from all operation system and make it valuable for analysis, okay? So this enables kind of diagnostic and basic predictive analytics as well. The technology was very expensive, right? Because it needs kind of significant upfront investment, because it use kind of powerful machines, right? So right after that turn, the big data era. The big data era means is kind of starting kind of I think 2008-10. So it was driven by the data volume exceeds the capacity of the that data additional data warehouses can handle, right? So that's why the Hadoop distributed storage and processing the NoSQL databases. Then the cloud also even make it kind of economically valuable for store petabytes. That's why we are in today, right? So the AI era, the machine learning and deep learning frameworks, the LLM models, something like that, right? So okay, so this is the transforming what is possible that organization or suppose they are not traditional. That means they are not obsolete. You can use that one, but it depends how the your use requirements is gathered, right? So let's move to kind of the standard data was big data, right? So this is a kind of uh, you know kind of uh, you I think you know about this one, but let's talk about this one because it will support you for your discourse. Okay, so the standard versus data versus big data, right? So the traditional SQL systems, right? So the OLTP means online transaction processing, right? System in your bank or supermarket, they are designed for structured and processed data, right? Every field has a type, okay, and every record has the same structure, and the schema is designed in advance and enforced on every write, right? This is why the schema and write approach guarantees the data quality, but it limits the flexibility, right? So, yeah, can you guys find it what is schema on read and schema on write? Can you put the answer in the chat actually? Can you find it what is schema on read and schema on write? Can you hear me?
Yes, sir.
Yeah, yeah. Can you find it? What is schema on read and schema on write? With the example, just find it, right? I will give you 5 minutes. Okay, yeah, thank you. So actually, you put the correct answer, right? So yeah, I think you can understand what's the schema on read and what's the schema on write, right? So again, I would like to say that in the traditional SQL system, the data schema is designed in advance and enforced on every write, right? So this is called schema on write. So it guarantees the data quality, but it limits the flexibility, right? So in the big data system, kind of a filter on this one, right? So they use schema on read, and the data is. Hello, can you hear me?
Yes, sir.
Okay. So the data is stored in raw or in a semi-structured format, or either the schema is applied at an analysis time, right? That means you can store data before you know you have fully decided how you're going to use it. It's a kind of a profound shift. Okay. So for example, let's say that the company stores the use action on a JSON event, kind of WhatsApp or Facebook, right? They do not know in advance every possible types of user interaction, right? So if new features are launched regularly to generate new event types, then with schema on read, the new event types simply the analytics define, they can inter add it, right? So and no schema migration is required, right? So in this case, actually the users also different. The traditional OLTP, the online transaction processing, the system are used by the business professional, the operational application kind of checkout system, billing system, CRM. In big data system, it's mostly used by the data scientist, the BI professionals, and who needs to flexibility to explore, experiment, and the discover, right? So okay, so the different in the user profile also directly impact on the infrastructure design as well, right? So operational system need sub-millions response time for a single record lookups, but the big data system need to process billions of record for the analytical queries, right? So these requirements lead this us to kind of completely different architectural choices, right? That's why I added this slide to know about the standard data versus big data, right? So again, we are moving to kind of a definition stuff, the big data. So you all know this one, right? So but I want to tell it again because concepts are much more important, right? So there are many difference of meanings that floating around about this big data, right? So but I think big data is a kind of data of whole scale, that diversity and complexity as new require architecture, then techniques and algorithm to manage that data, right? And where we extract value from it. Okay, so notice actually that the actually it does not say big data is simply not lots of data, right? A petabyte byte of kind of sensory kind of stuff, right? The okay, the big data is about to combine of scale, again the diversity and the complexity that break down some traditional tools, right? The defining when we define the characteristic that is data exceed, where existing technology can store, manage, and process efficiently. The efficient is the key, right? So for example, you might able to brute force that you work through the problem with enough hardware, right? So, but it's not a kind of a sustainable engineering solution. Okay. So actually the other thing is actually we need entirely new classes of algorithms, streaming algorithms, uh, because you know at some points now the exact algorithm is become too slow, and we need to have kind of a entire new of class of algorithms, right? So this is what actually we talk about the required new architecture technologies and algorithm to handle the analysis and enable extraction valuable insight from the hidden knowledge of massive data set kind of stuff. It's a kind of a floating definition, but I would like to add this kind of a characteristic of high diversity and complexity of the large scale, right? So yeah, this is data versus big data characteristics. And okay, again, so the first difference is kind of a data type, right? So the traditional system handle structured process data, kind of the records in the rows and columns kind of stuff, right? But the big data actually it must handle this kind of tree, right? The structure from the databases, the semi-structure like JSON and completely unstructured like images, video and stuff like that. So the second difference is kind of schema approach, right? We talk about this one, the schema on write and schema on read. Okay. The third one is kind of agility one. The traditional systems are less agile because they are require front upfront schema design, right? And manage to that migration, right? The big data is actually it should support to accommodate new data sources, new formats without pre-planning, right? So again, we talk about the users, the data scientists and BI professional stuff like that. So these are the data dimensions, right? So kind of the volume, velocity, variety, and kind of stuff, right? So we talk about this in the 5 E's, and originally it's 3 E's and later on 5 E's. We talk about twice, right? So we recap on the last lecture as well. So then, so this is kind of a technology stack, right? So in traditional data system, so kind of let's say uh, the traditional data warehouse in one kind of era. So it was built on the relational databases, OLTP and OLAP system, right? The standard SQL queries and tools. The typically, the single large server or kind of a small cost of powerful machines, right? So scaling was vertical. If you need a kind of more capacity, you bought a new bigger server, right? So the big data technology, so it's fundamentally different. So storage is kind of hundreds and thousands of accommodation servers, kind of then the processing is parallelized kind of frameworks like Hadoop and Spark. Then the databases are specialized for specific for workloads. So we are going to talk about that on the column store databases, key value store info, caches, the document one. So in the next few slides, we are going to talk about this, right? The graph databases and stuff. So then the decision support layer also kind of involved dramatically, right? So kind of the traditional data warehouses queries by BI analytics tools like Crystal reports. So I did kind of Crystal reports kind of in my intern. So I used .NET kind of stuff. I think there's a NuGet package for do Crystal reports, right? So it's not obsolete, it's traditional way. So the modern big data analytics use kind of Python and data science, stacks, distributed machine learning framework, like TensorFlow, kind of what PyTorch, and interactive notebook environment kind what Jupyter. So this is kind of a I mean the the evaluation of the decision support tools, and how it support to the big data era, right? So actually, this all means naturally to use NoSQL, right? NoSQL database are not kind of replacement of the relational database, right? They are especially additional kind of a toolkit. Okay, so they exist because certain workloads, right? Kind of high velocity writes and flexible schemas, then massive horizontal scaling, graph traversals. Actually, these requirements are fulfilled with the NoSQL database inventions. Okay, so actually we came across kind of different kind of stuff, and it's I know that it's a kind of boring, but what I will do also, I am telling you, okay, what is decision pattern understanding kind of stuff, prediction. So this kind of data complexity kind of stuff. So I'm also not like to kind of, okay, put the lecture slide and explain it, but we need to focus on these factors, right? We are talking what's caused that evaluation of the big data era, right? What are the reasons, right? So what are the challenges, and what are the type of analytics that use force us to make it kind of a new infrastructure? Okay, those are the things that we talk about, right? So if we talk about, the discovery patterns, then we talk about the pattern understanding, the challenges, prediction, and we talk about the descriptive analytics. Those are the analytics. What are the prescriptive analytics, right? So even, we talk about the value versus difficulty for the each analytics, and we talk about, the big data and big data definitions, and the dimensions, the traditional data, and the reason why I use this knowledge for you is to understand what causes the new technology stack for the big data, right? What can we do from the traditional infrastructure, and what can we do from the new infrastructure, and what's the bottleneck to solve this problem, right? So these are the kind of concepts that I went through to understand you, to give the knowledge what causes this new big data infrastructure. Okay, so yeah, from onwards we are going to talk about some concepts, the acid properties, the base theorem and stuff. And okay, so we are going to deep dive into each concepts as well. Now it's 9:45. Mm, okay, at 10 let's have a break, right? So okay, now we are going to talk about acid properties, right? So there are four acid properties: okay, atomicity, consistency, isolated, and durable, right? So that's why the acid came from with the first letter of the word. Um, okay, so this is a kind of a summarization. Yeah, the whole transaction completion, none of the complete kind of atomic one. The consistent one is kind of the, the transaction transform the database into one consistent state to another, right? So the isolated means result during the transaction is not visible to others until the transaction commits. Okay, then durable means results are committed transactions that survive system failures, right? So it should be data is should be persisted permanently. This is a kind of a summarized version. So this is a kind of in-depth one, right? So yeah, so let's deep dive into kind of atomicity and consistency, right? Because understanding these properties in depth, it will help you to appreciate exactly what you have given up when you have moved to NoSQL system, right? And why that trade-off is kind of something like worth making. Okay, so so atomicity means all or nothing guarantee, right? So for example, if it's implemented in a database engine, it's implemented kind of inside kind of right right load, something like that, WAL I think, or redo log also said. So before any changing is applied to actual database, the record of that change is written into a log or durable storage, right? So if system crash or if system crash in the mid transaction or something, like if it restart the database, so it identify which transaction were incomplete and rolls them back. Okay, because we write in a kind of a write ahead log. Okay, so okay, I will tell it again. The atomicity means the database engines implemented this atomicity concept to a kind of a write ahead log. It's called WAL, and before change is applied to a actual database table, a record of that change is written to a log on a durable storage, right? If system is crash um, in a kind of a mid transaction or restart database, something like happen. So the log is support to find identify what transactions were incomplete and rolls them back. So this gives you atomicity guarantee even in the face of hardware failure as well, right? So then the kind of, let's say, the cost of the atomicity is kind of overhead, right? Because every write operation requires first writing into log, then writing into actual database, right? So for high write workload, say kind of more millions of transactions per second in kind of e-commerce platform. So this kind of a double path kind of writing stuff, right? So this is the one of the reason why the NoSQL databases coming up, and it lacks the kind of atomic guarantee and can be archive kind of achieve kind of a high write throughput, right? So this is a kind of a definition how it matters. You can see how it works, right? So a writer log, the transaction managers that track all the kind of stuff I explained you, right? So then the other thing is consistency, right? Consistency in the ACID sense is about kind of enforcing the business rules through the database constraint. And you know the database constraint, right? So primary key ensures the uniqueness. Then foreign key ensures the referential integrity, and check constraint enforce a kind of a value ranges, not null, kind of preventing the missing required data kind of stress, right? So every transaction move to a database from the one valid state to another valid state, and all the integrity rules, constraint, and the relations are preserved throughout. Okay, so these are involved in enforcing every single right and synchronously before transaction is committed, right? So the cost of this consistency constraint is that it must be checked on every write. So before check it, we need to check the constraint, right? So is it a primary key or kind of a not null kind of stuff, right? For a table within a millions of rows, checking foreign constraint requires a lookup kind of a reference table, right? So at high volumes of data, the lookups can be performance bottleneck. Okay, so this is why it matters, and why what is mean by consistency. So the other thing of the acid properties is kind of isolation and durability. So isolation and durability also other two kind of acid properties mostly um, challenging by the big data workloads, right? So isolation deals with the problem of concurrent access. Okay, so for example, in any database, hundreds of thousands of transactions may be running simultaneously. Without isolation, these transactions can interface with each other, right? In a kind of a catastrophic, I mean the catastrophic way. Okay, so for example, let's say like, right, so there are two trades. One trade is trade A, other one trade is trade B, right? So uh, trade A read a value, okay? thread B also read the same value, right? What thread A is doing, it modifies the value and write it back, right? So the thread B also modify using a stale read and write it back, okay? So A also read the value, thread B also read the value, A modifies C, write it back, but the thread B also modified it using a stale read and write it back. So overwriting, what will happen is it's overriding the thread A's change, okay? Now think about this scenario in a kind of a high frequency trading system or booking platform, can be account balance as well. So it could be kind of a incorrect account balances, and it's not a kind of a good at all at a kind of a high frequency trading system, right? So the major kind of stuff is kind of let's say uh, okay, so trade-off with the isolation is kind of a performance, right? So for example, the sticks where the transaction are executed at SQL, it provides the guarantee, strong guarantee, but limits the throughput service, right? So most production databases are kind of weak of isolation level. So read committed or repeatable read. Okay, so that allows more concurrence at the cost of same anomalies, right? So this is why you need to taste of the consistent performance and the trade-off that define the NoSQL designs, right? So this is what happened in the isolation, and so implemented kind of a looking stuff and kind of the multi-version of the concurrently control, as I said, the isolation level read committed, and so it can be of a kind of a looking for the repeatable update of the same record, right? So then this is called durability. The other one, durability means committed data at the serve time, right? If it's fails, that data committed should be survivor, right? So the implementation involving write height login, and we talk about the write height login in the first atomicity one, and it to persist changes before acknowledging the commit, plus a regular check-in point to apply the log, actual data on the files, right? On a crash recovery, data replace the log into restore the committed state, right? The cost of the durability in a distributed system is kind of a replication latency kind of for committed transaction to a truly durable, the write must be confirmed on a multiple physical nodes, right? So the time taken for that cross node confirmation is kind of typically takes around 1 millisecond on a local network, and directly it's actually direct adds to a kind of a latency. So that's why the durability is there. So once transaction is committed, it changes up permanently stored, right? So the data persists even if a event of a system crash or power failure, something like that. So why it matters is kind of the guarantees that come from business transaction, like completed payment never lost due to infrastructure failures, right? How it work is, so it's achieved through the right hand of WAL and replications, then durable storage mechanism that flush data into a disk before acknowledging the commit, right? So those are the things I need to deep dive into kind of acid properties, atomicity, consistency, isolation, and durability. Okay. So let's move to the CAP theorem, but let's take a break and let's meet around kind of 10:20, right? Okay, let's take a break. Hello guys, can you hear me?
Yes, sir.
Okay.
Yes.
මේ කොපට සිංහලෙන් කියන්න කාට බෝරිං වගේ ඇති මේ හැබැයි මේ concepts ටික දැනගන්න වෙනවා. මොකද අපි step by step තමයි මම මේ ඔයාලව big data infrastructure වලට අරයන්නේ. එතකොට මේවා ටික මමත් ටිකක් වෙනවාට කැමති නෑ තමයි. obviously මමත් ස්ටුඩන්ට් ඉන්න කාලේ ලෙක්චර් එක අහනවා. right මේවා දාගෙන ඉඳි පොඩක් බෝරින්. හැබැයි සමහර වෙලාවට මේ දේවල් ඔයාලට ඕන වෙනවා. මොකද මම one example එකක් කියන්න. මම ෆේස් කරා ඉන්ටර්විව් එකකට මයිග්‍රේෂන් වෙන ඉන්ටර්විව් එකට මම ඒකේ ස්ටෙප් 3-4ක් ගියා but at a some point මන්ට ඒකට යන්න බැරුණා right so ඒකේ first step එකේදී එයාලා මේ මෙන්න මේ cap theorem acid properties ඔය ටික in depth අහුවා මගේ right so මම ඒක in depth හරියටම වෙරිෆයි කරා මට ඒලා බැරුණා එතකොට තමයි මට තේරුණේ මෙන්න මේ concepts ටික ඕන වෙනවා මොකද මේ concepts වලින් තමයි අපි දැන් ඔයාලට හිතුවොත් එහෙම AI tools right chat GPT හරි මොකක් හරි එකට මම දන්නවා ඔයාලා කොහොමත් දැන් අපි ඉන්ටර්විව් කරන කට්ටිය ගත්තාම ඒ කට්ටිය ගොඩක් ඔයාලගේ ඊර එකත් එක්ක ඒක ඕකේ right so අපි ඉගෙන ගන්න කාලවල ඔය chat GPT right නැත්තම් එතකොට ඔය Claude වගේ AI ෆැසිලිටි එකක් තිබ්බේ නෑ අපි කරන්නේ මොකක් හරි එරේ එකක් හොයන්න ඕන වුණාම අපි කරන්නේ එක්ක Stack Overflow කියලා සයිට් එකක් තියෙනවා එක්ක ඒකේ හොයනවා නැත්තම් රිසර්ච් පේපර් කියවනවා නැත්තම් ඒ බග් එක කවුරු හරි දාලා තියෙනවා නම් මොකක් හරි හිතන්න මොකක් හරි වෙබ්සයිට් එක එක්ස්ප්ලেইন කරලා අපි ඒක කියවනවා එතකොට Microsoft එකේ software එකේ documentation කියනවා එතකොට ඒ කියවද්දි අපිට අහුවෙනවා ඒකේ basic concepts ටික right එතකොට අපි මේ problem එක solve කරන්නේ basic concepts එකේ ඉඳන් අපි හොයනවා කොහෙද මේ issue එක තියෙන්නේ කියලා okay so that's why I need to know these basic concepts I know that it's also kind of a boring stuff but you must listen the lecture again and try to understand what I'm going to tell it so now you have easy to understand right because if you have any question you can just copy the entire stuff and put it in a kind of a chat GPT and explain with a kind of a example okay they will explain to you right so එක තමයි මම කිව්වා හරි lucky මොකද ඔයාලට ඉගෙන ගන්න sources ගොඩ ඉගෙන ගන්න lazy right අපිට ඉගෙන ගන්න ටිකක් අපිට පොඩ්ඩක් effort එකක් දාන්න ඕන ඒ effort එක තමයි අපිට මොකක් හරියක් ඕන වුණාම මේ අපි ඒකට A to Z හොයන්න ඕන නෑ. හැබැයි ඔයාලට chat GPT හරි මොකක් හරි එකකින් A to Z ඒ knowledge එක ඔයාලට ගන්න පුළුවන්. with a one kind of a one prompt, right? but අපිට එහෙම නෑ. හැබැයි අපි මේ විදිහට යමු. මොකද ඔයාලට ගොඩක් concepts කියලා දෙන්න වෙනවා. මම මේ ඔයාලට කියලා දෙන concepts ඇත්තටම සමහර ඒවා deep, right? ඔයාලගේ level එකේදී මේක expect කරන්නේ නැහැ. මොකද මම කලින් lectures වල බලද්දි මේක නිකන් just අර අපි කියන්නේ නිකන් උඩින් කියාගෙන යනවා වගේ. හැබැයි මං හිතනවා ඒක දැන් වෙනස් වෙන්න ඕන කියලා. මොකද හේතුව ඔයාලා ඉන්ඩස්ට්‍රි එකට යද්දි හරි කම්පිටිටිව් ඉන්ඩස්ට්‍රි එක. ඔයාලගෙන් දැන් එක්ස්පෙක්ට් කරන්නේ නැහැ යාලා ඔයාලගෙන් පාස් අවුට් වෙන නොලෙජ් එක. රයිට් මොකද ඔයාලට එයාලා එක්ස්පෙක්ට් කරන්නේ ඊට වැඩි දෙයක්. ඒ හේතුව තමයි මේ AI වලින් එක්ක ආපු ඉවොලුෂන් එකත් එක්ක හැමදේම දැන් ස්ටෑන්ඩඩ් වෙනවා. රයිට් එතකොට හැමදේම සිම්පල් දැන් ඇප් එකක් ගහන්න ඉස්සර අපි ගොඩක් කල් යනවා ඇප් එකක් ඩිසයින් කරලා ඒකට හිතන්නකෝ ක්ලීන් ආකිටෙක්චර් වගේ මොකක් හරි ආකිටෙක්චර් එකක් දාලා එහෙම කරගෙන යනකොට නැත්නම් data pipeline එකක් හදනකොට හරි ඒ හැමදේම දැන් one step right මම කිව්වොත් එහෙම සමහර වෙලාවට මම දැන් Claude එකෙන් මොකද මම අවුරුදු මම මේ සිංහලෙන් කතා කරලා කමන්නේ නැහැ නේ it's it okay to speak in Sinhala hello hello can you guys hear me
Yes, sir, we can.
okay is it okay to speak in Sinhala or you want to listen English hello okay so yeah so I'll explain in English right so what I'm going to say is even now when you give a kind of a access token of the cloud so then ask Claude to find the issue in this infrastructure setup in the cloud they will find for you right so in the very first time we have to deep dive into that the diagnosis matrices and stuff and see what's happened right but right now it will find for you So that's why I'm telling that you must need to know these concepts. And yeah, let's move forward. So let's take a break on this one. And after 10:20, let's move with the cap theorem, right? So see you guys.
Yes, sir.
Okay, yeah, thank you. So yeah, now let's move forward with the cap theorem. And so yeah, it's a kind of most famous and kind of most frequently used theorem in the distributed system of the computer science, right? So you must understand that this is for kind of a distributed system, right? So it's called the Brewer's-Cup theorem as well, right? So I want to spend some time on this because it's a kind of a foundation on which every NoSQL basis design decision is made, right? So CAP is standard for actually um, consistency, availability, and partition tolerance, right? This give it a minute, please. Oh, okay. So this is a kind of a summary one, but yeah, I will explain from the beginning. Okay, and CAP is standard for again consistency, availability, and partition tolerance, right? So this um it's a kind of state. It's formally this theorem states that in a distributed system, the meaning a system that runs across different multiple network nodes, and you can only guarantee two of these of three properties simultaneously, right? That means it states that in a distributed system, so either you have to maintain CA or AP or CP, right? So when you had a kind of a third, you have to give up one of the other, right? So before I explain each property, let's explain why it matters, right? So for example, your production database that serve in a real business must need to handle failures, right? So it's not optional one, right? So network fail, server crashes, data centers have power outages, and so the system that cannot tolerate failures is not a kind of a production system, right? So the Capsi theorem tells us that when fails happen, and we must make a choice, right? That choice define is what kind of database we are building. Okay, so the consistent in the cap, um, you know, um, since that you receive the most written no, that means most recent right or an error. So kind of stuff, right? So okay, so every node in the cluster, when queried, it returns same value at the same time, right? So for example, if I write value to node A, so immediately it just read the value from node B as well, right? So kept consistent, the consistent system guarantee, okay, I get the updated value, right? So this is a kind of overall idea about the cap theorem, and we are maintaining because we are optionally not optional on the we have to handle failures, network or server crash, and so when the theorem tells that when the failure happen, we must make a choice, right? The choice is defined on what kind of database we are building. Okay, so okay, this is uh um with the continuous of the cap. um Actually, this is define the consistency. Wait a minute, did I miss something? Yeah, no, right? Definition. Okay, this is consistency, right? So you can see the traditional relational database management system, prioritize consistency and availability, and trade-off means actually to maintain consistency, the system may delay or reject request when some nodes are out of sync, right? So if we say that one node is down, so it can delay for the system because so it will take some time to spin up node again, right? So if it can reject the request, right? So definitely this causes the latency spike or availability loss in during the partition, right? So what it guarantees actually any read operation the most recent write to error, right? So it's not a still data, right? So every client always see the same view of the system, right? So if you go to the availability and partition tolerance, the other C and P, A and P. So availability means every request receive a response, right? It can be a success or failure, but always a response, right? So not please wait, okay, something like that. We are going to synchronize this node or something like that. It's not happen, right? So every request receive a response. The system remains operational responsive when even when individual node is failed, right? So trade-off in here is actually response may contain still or outdated data, but the system does not wait for the all nodes to synchronize before respond, right? This is the trade-off. So for example, the Cassandra or Couchbee, right? This database stay responsive during the network failures and the setting that some nodes may survive sidely or data, right? So this is called availability, right? Always an answer, um, always immediately, right? So the key difference on the consistent is an available system, will respond even that response contains slightly still data, right? So I told you that one. So and in it priority is being a responsive over being kind of perfectly accurate, right? So from a user experience perspective, getting kind of, let's say, 99.9 accurate in 50 milliseconds is often better than getting a perfect accurate results in 5 seconds, right? So that's how it defined. And if we move to the kind of partition tolerance one, so it means that a system continues to operate if it's a kind of a network failure, right? So for example, that we talk about node A and node B, right? So what happened is network failures split the cluster into isolated group and they cannot communicate each other, right? That means node A cannot reach to node B, but the system keeps running and despite the partition, right? So there is a kind of a critical insight, right? So any real distributed system deployed over real network, and if network partition will happen, if the networks are unavailable, so it can be happen, right? So if that means, for example, uh, it's not optional, right? So for example, I must say that networks are unavailable, sometimes routers are fail. So there is a network partitions can be happen, right? So cover, even in the cloud availability also, zones also have outages, right? So partition tolerance is not an optional one. It's a necessity. So in the practical scenarios, the cap trade-off is not whether to be partition tolerance or rather than, partition, of course, do you need to choose partition consist, that means prioritize consistency or availability with the partition tolerance, right? This is a kind of thing that you must use. Actually, this is a kind of a visualization stuff, that what is consistency, availability, and partition tolerance. And this is a kind of CA, kind of MySQL. It have consistency and available, not partition tolerance. So consistency and partition tolerance have kind of MongoDB and stuff, and availability and partition tolerance have Cassandra kind of stuff, right? So so again, if you um talk about the criterion, so C for consistency, A for availability, and P for partition tolerance, right? So in distributed system, you cannot guarantee all three at the same time. Okay, so consistency means you all users see the same data at same time, and you returns the latest value, right? So to keep that in the trade-off in here in the consistencies, keep the strong consistency, you have to sacrifice availability, right? That means you have to sacrifice availability to keep consistency, right? So either two of the three you must use that one, right? Either CAO, CP, or AP, right? So in CP system, what happen is actually its system ensure you know all nodes have the same data, and if there is a network issue, set system may refuse the request, right? So for example, yeah, this is HBase and MongoDB, right? So there are pros and cons there. The pros is kind of no stale data in here, right? And accurate results. And cons are kind of, system may become unavailable, right? So availability we remove from this one, right? It's C and P. And system and high latency, right? Wait for synchronizing. So for example, if we say that there's some kind of node is down, it's available, wait for the sync up options, right? So the AB system is reducing consistency, right? That means system always stays available, but data may be kind of temporarily inconsistent, right? Because we remove consistency from in here, right? So the as in the DB kind of Cassandra. So it's the processing here is actually it's always responsive, and it's very fast, right? So the cons part in here is actually it's user may seeing different data because the consistency one is not in here, right? So that's how we deal with this one. And so if we talk about the real-time example, I must say that okay, so banking system, right? So for the banking system, we need consistency. So balance must be exact, right? So better to fail the request than showing your own balance, right? So then social media need availability, right? So actually, for example, it's better to always respond, right? Even if a slightly outdated, for example, let's say that like comments can be slightly delayed, right? It's all right because the social media it's needs availability. So and yeah, that's the thing actually we need to talk about. And okay, so this is what we talk about the cap theory, and now let's move to base, right? So if we what differ from the cap is actually cap tells us theoretically possible in the distributed system, right? So but the base tells us how the NoSQL database actually behave in practice, right? So base is kind of we can take it as kind of a opposite of acid, I think. So while and this can be seen the concepts have captured more granularly important, right? The based. So um basically available, soft state, and eventually consistent, right? So yeah, it's a relaxed alternative of the acid of the scalable distributed system, right? So basis basically available mean that actually um the system is designed to be available almost at time, right? So note that word basically, okay, it acknowledge that no system is kind of 100% available. It's basically right. So network partition can happen, hardware fails, and the different from the fully acid system is how actually how the fails are handled, right? So the base system prefers return the response potential is stale there or waiting in an error or waiting, for the synchronization, right? So, so you can see in here as well what it means, what I tell you already. So, every request is your response, success or failure, and um, the returns data may not be the late version. The system attests temporary inconsistent in exchange or remaining always on, and its continued operation. The system keeps running in during the network failure as well, and it does not block for all replicas to be synchronized, right? So, for example, so if you talk about the WhatsApp, right? So WhatsApp also, I think they use base design for message delivery, right? So first, when you send the message, and let's say that the phone goes offline immediately after sending, you will see a single tick, right? So, but when the phone reconnects, you will see the double click delivered, right? So when the recipient reads that one, you will see the blue tick, right? It's read. So the tick represent the message gradually propagating through a system of consistent state, right? The this is basically available in action, right? The system confirms that the reset at each step rather than waiting for end-to-end consistency before responding, right? So that's a kind of a example. So about the base design on message delivery, right? The sophisticate means actually system does not maintain strict consistent at all time, right? So data may be kind of a situation like kind of a what a flux, right? So different replicas may be temporarily hold different versions, right? So this is acceptable because the system will, eventually cover it, but at any moment you can assume that all the nodes have same way, right? So okay, so actually uh, okay, so something like this, right? So if you add a product on your whitelist on a kind of, let's say, Amazon or something like that, immediately open on the app on a other device, and you might not see the new items because of the fraud of the second fraction of a second, right? So if you add a product on a whitelist on Amazon in a one app on the other device, if you move to the another device and see, you will see the new item there, but it's get a kind of a fraction of seconds, right? The whitelist data in a kind of a soft state, right? So it has been written to some nodes but not replicated at all, right? So within milliseconds the replication can be catch up, right? So actually, it upset this brief inconsistency because it allowed them to provide fast write in the global availability. So, right kind of Amazon stuff, it has a lot of you know fast writes and availabilities, no. So, kind of milliseconds of synchronization delay before confirming the whitelist would be, far more annoying than the kind of 50 millisecond delay, right? So that's where the new item briefly does not appear on the second device, right? So again, if you go to the software state, the system is not strictly consistent at all the time. The data can be changed over without in new one, that it is in the flux, and you know caused by asynchronous replication across distributed nodes, and the different nodes may be temporary hold different versions, right? So what it happened in here, so this is a kind of a practical implementation as well. So the sophisticates actually it should be carefully application design, right? So the course must be written kind of defensively, so never assume that the data you wrote moment ago will immediately visible in everywhere, but this is a kind of a discipline that traditional SQL development does not require, and it's a reason why some engineers initially find a SQL system, right? So the base other one is eventually inconsistent, right? Okay, so eventually consistent mean all the replicas will be coverage to the same state once update is propagated, right? That means E in the actually it is based on no, so E in the E in the base, and it's probably kind of important concept in the NoSQL database design as well. So let's the eventually consistent again. It means that no new updates are made for all piece of data, and all replicas will be coverage to the same value eventually, right? This word eventually is kind of doing a lot of work in here. So in practice kind of stuff, the coveraging typically happens within milliseconds to seconds in a healthcare class, right? So for example, say the DNS name system, it's mostly wide use, eventually consistent in the world, right? So even though people do not think it has a database, right? So when you update the DNS record, the domain name system way, say that change in your IP address, so that changes propagate to DNS server wild worldwide, right? Over a period of time. Right? So it may take minutes, right? So if a user Sri Lanka try to access the website kind of stuff, let's say, then it may be directed to all IP, but in a user in another country might see the new IP, right? So both are valid. So they are just seeing the system at different points, and it's kind of a coverage towards the consistent state, right? So this is what it guarantees, and the trade-off is kind of no need for immediate synchronization. That's what I explained in the DNS record example, and no need of immediate synchronization before responding, and suitable kind of for system where short delay seen the latest data is acceptable, right? So yeah, the example is social feeds and analytics stuff, and there are some practical examples as well. So DNS propagation. Okay, so this is the kind of a one that I tell you, and yeah. So the challenge in the of this application developer is writing a code behave correctly under eventual consistent, right? So consider a kind of a bank scenario. So where customer transfer money between two accounts, then immediately if they refresh their account in the summary page, so with the strong consistency, the updated balance is guaranteed visible, right? So with the eventual consistency, there is a window. So possible kind of small millisecond, the VAR would be my still show the old balance, right? So the correct engineering respond to is not either eventually consistency because it designed your experience and your data model to accommodate, right? So even though it's a kind of a eventual consist, you must uh, need to kind of develop the code in a kind of a careful thought, right? So actually, it's not a kind of a bug, right? It's not the system will cover is that one. So, but you know, design your application should knowing this one, right? You can build highly scalable system that handle billions of operation without sacrifice the correctness of this case matter, right? So this is the base transactions, and this is the summary of the base and the basically available of state and eventually state, and uh, okay, so this is what the summary tell you. It's a kind of contrived as the opposite of acid, and this is basically available again the system guarantee available of the data as it required by the CAP theorem, and every request receive response to a data return may always not be reasoned in state, right? So soft state means the system could change over time even without a new input. The data may be in a flux, right? The replication and consistency mechanism propagate update across all the nodes, right? Eventually consistent, we discussed about that, and the system will eventually become consistent once it store retrieval stop receiving a new input, right? So the replicas will coverage the same value enough time and without requiring, asynchronous coordination, right? So understanding actually both acid and base and the cap traders are connected, right? So it gives the kind of vocabulary and the framework to make intelligent database selection decision, right? So in the rest of this lecture, we will try to see apply this framework for specific database types, right? So that's the end of the base, and yeah. So we are move forward with the okay. So no SQL, right? No SQL means no SQL, right? That it means that actually it's stand for not only SQL, right? So meaning the the databases complement SQL database rather than replace them, right? So so actually for when you talk about the NoSQL databases, it was kind of around I think right after 2006, right? The big companies like Google, Amazon, they hit the ceiling what the relational database that could scale to, right? So then the companies they invented kind of all created a solve a specific scaling problem that traditional relational database management system could not address, right? So what these database have in common is what they gave up, right? So they are full burden of ACID transaction rigidity and kind of predefined schemas, SQL query languages, and not because these are bad, right? So but because at a scale the maintaining all these three of the simultaneously was impossible kind of stuff, right? So it's important to understand um actually why NoSQL is kind of not a kind of a single thing, right? NoSQL not a kind of a single thing. It has family of database type, right? So it is optimized for each specific data model across the each access pattern, right? Kind of column stores, then document stores, key value stores, kind of stuff, right? So all these are kind of fall under NoSQL, but they are different, right? So kind of like the car is different from bus now. Likewise, they are also different, right? So the right choices depends on the on your use case actually. So yeah, in here it says that the same thing, right? So the embraces the horizontal scale across the community of the hardware clusters, and it designed for high velocity, high volume, and high variety of data. And it eliminates the burn rigid upfront schema design kind of schema as a right, then reduce the overhead of ACID transaction, so better scalability. Those are the things that we need to know about the noise scale, right? So if we talk about the characteristics of the noise scale, so so before we deep dive into kind of a NoSQL database side, so there are some generally characteristics, right? So availability, the best effort, and weak consistency or still data is okay, kind of characteristic, right? So let's talk about this one by one. So first thing is actually weak consistency, right? So NoSQL system, often return data that may not slightly out. So this trade-off is enable you massive scale, right? It means that the application must be designed to tolerate reading the data that may not reflect the most written right? So this is a fundamental shift in the programming model as well. So in SQL, you will write what you wrote, right? So in many NoSQL system, there will be a kind of a window. It's a small window, millisecond window. and it can be accepted, and the Windows must where you might not. Okay, so the availability means the system is engineered for stay responsive when parts of the infrastructure fail, right? So this is a kind of archive through the replication, and every piece of data is stored in a kind of a multiple nodes. Okay, and if one node fails, the other serves request, right? So this is like kind of, let's say, Cassandra, no single point of failure can tolerate the entire data center and fail, right? So so actually, there is a one incident in AWS EC2 instance failure. So, but the Cassandra clusters has several microservices continue to operating without interruption, right? So the replication factor ensured that the data on the fail node was not also available on multiple healthy nodes, right? So what happened is the system is actually automatically routed the request away from the failure node, and the nothing happened to this application runtime, right? So the other factor is best effort. So that means the operations are attended optimistically. If they are failed, the call handles the recovery rather than the database blocking, right? So that means actually the system will try its best to fulfill the request, but not always succeed, right? This is different from the SQL databases where failed operation return as an explicitly error. The state is guaranteed unchanged, right? In NoSQL system, especially those is the actualization replication some kind. The write may be confirmed to the client, but not yet the persisted on all replicas, right? So application might design for this one, right? So then other one is the the what's this approximate answers are okay, right? So in analytics, near correct answer available in millisecond is actually more value than the perfect answer in hour, right? So this is a kind of a characteristic of a NoSQL system. So for example, some big data queries engine can trade precision for speed, right? So kind of stuff. So sometimes it will take days to get the final answer. But for example, if we can get a kind of a answer approximately correct, that would be worth, right? In a milliseconds rather than actually seconds as well, right? So so these are the kind of stuff, and this is simple and faster because we remove the acid overhead and the rigid schemas and complex joins. So leads a kind of simple code and paths. So it dramatically low in latency, right? So then um, optimistic concurrence, right? So conflicts are detected and resolved after the fact rather than using logs, and that serialization access and limit the throughput kind of stuff. So these are the some NoSQL characteristics, and now we can move the NoSQL database types, right? So there are some types: column store, key-value store, document store, and graph databases, right? I think some of you have experience on these databases as well, but let's kind of have a this discussion from the beginning, right? So the fundamentally actually they are different data model, and the data model determines which problem is suited for, right? So there is no universal best NoSQL database. It depends on the use case, right? So there is only one database for specific access pattern, right? So column stores actually it organize data by columns rather than by rows. Okay, so the traditional database store field one record together, and column store all the values on a one field together, right? This is seemingly actually simple change, but it has profound implication of analytics because every query touches only one or two column. Even 100 read is 2% of data, not 100%, right? So there is a kind of explanation in the key value. Yeah, column store databases. I have added some deeply direct informations as well. So these are kind of a quick recap, right? So again, the key value store, right? It's a kind of data store as a kind of a pairs, like a dictionary, right? You know that key and value. So value can be anything, can be string, JSON, kind of a stuff, and you can retrieve the value in constant time regardless the database size, right? So then the document store. Document store is a kind of a schema free, right? MongoDB, the famous one. So each document can be structured, semi-structured, or unstructured, right? It can have its own unique structure, right? So it's typically can be a JSON or BSON, right? So actually with its own field nested structure, and unlike actually key value stored, the document or stored is you to query and index on the field within the document, right? So that's a special feature as well, right? So um okay, so the other thing is actually graph database, right? So it store nodes, edges, properties, and replace the entities of their relationship, right? So actually, for example, the fundamental difference from the relation database that the relationships are first class citizen that is stored directly in a database structure but not retrieved at query at the joins, right? So for example, linking, right? The linking, you may know you the feature of the power of the graph database, right? So they use the graph database, the you know there's a query, let's say that who are the friends of friends, not already my friends, right? So you also something like that in the Facebook also you experience that one, right? You are who are the friends of my friends, but they are not my friends, right? So it's a kind of a graph traversal. Okay, in a relation database, kind of a if you talk about relational databases, it requires kind of join operation, right? So in the graph database, it's kind of a optimized traversal, right? It's a natural and it's a kind of a fast operational, right? So that's why the graph database is important at kind of a social media stuff implementations, right? So before that, let's move to the kind of a SQL database, the data definition language. You all know this one, right? So what is DDL, the data definition language? So it used to define and manage database structure or schema, and it is specify how data is stored, organized, and related. And schema is defined before the data inserted, schema on right. So this is called kind of a DDL and concepts, right? So it's the understanding actually of the DDL will give you kind of a clear contrast with the schema-free approach of the NoSQL, right? So actually, the set of SQL commands it used to define, modify, and delete database structures, tables and constraint likewise, right? So the create table is statement is everywhere. Everything is beginning, right? So you can specify the table name. Each column has the data type and the constraint. And one is design. Every row insert into table must be concerned exactly of this structure, right? So I think you know that one. So the power of the DDL constraint is kind of they are enforced to at the database level, right? Not the application level. Even a kind of a buggy application tries to add kind of invalid data, the database will be rejected it, right? So it's a kind of a defense actually. So these are the some kind of DDL operation, that time, the create or the drop, truncate, comment stuff, right? And this is kind of related to constraint and data integrity. So constraints actually enforce accuracy and consistency of the data in the database. So the primal key, foreign key, not null, unique, check, those are the stuff, right? So and the unique constraints are actually, you know similar to primary key, but they allow null, right? So it can be applied on a combination of columns as well. Okay, so yeah, these are the some consideration, right? So then this is triggers and access control, right? So stored procedures stuff, right? So triggers are actually stored procedures that automatically execute in a response to a data modification event, right? So and automatically when event occurs, kind of, let's say, insert, update, delete, or in a kind of a specific table, right? For example, we have audit login, data validation, and cascading updates, right? So let's say that a bank transaction table has trigger run every insert, right? So that means the trigger checks whether the transaction um amount is kind of, let's say, kind of 1 million. So if it does, it's automatically inserting to a alert table, and it monitor and by the compliance team, right? So this number of large transaction are always flagged to review, kind of large transaction. That means, let's say, over 1 million, we need to track it down, right? So we can use this kind of stuff to track this down. Okay, so actually stored procedures are kind of similar but more general, right? So they are pre-compiled SQL programs, and stored in the database that can be called by applications, right? So then they are useful in calculating kind of complex operation and reduce network round trips and kind of stuff. Okay, so the access control one is kind of the given user specific permission, like select, insert, update, delete, right? So revoke means remove permission from the user's role, right? And the roles means the group of permission into a role and easily manage, right? The roles. Okay, and so this is why the access control matters. Actually, the controllers, it controls the who can read, write, or modify data, and you know minimize the attack surface, right? So it ensures the only authorization users can execute sensitive operation or access the kind of confidential tables, right? So these are the things. Actually, the in the NoSQL world, the access control also important, but it implemented differently, actually. So the for example, the Cassandra did uses role-based access control with a k kind of key space level, and table is level is permissions as well, right? The MongoDB also use role-based authentication with the collection level granularity, and so this is the principle is least privilege, right? Need to know access, right? So this is how actually NoSQL world also use this as access control. Okay, and okay, now let's deep dive into the column store database, right? Okay, so now let's start with this one, and sometime this called as white column stores as well, right? The column store, but because they represent the perhaps most significant kind of departure from traditional of oriented storage, right? To understand column store, first you need to understand how the rows store physically in store data, right? So in a row store, what happened in the traditional database users is all fields of a single record are stored sequentially on a disk, right? So, for example, record of one's data altogether, records of ID, two data of altogether, and when you read a record, you have to read everything. Okay, but is there any? Okay, like this, right? It is stored like this. Okay, but when you need to read it, you have to read each row, right? So then okay, so in the column store one, the storage of organization is kind of a flipped stuff, right? So all the values for column one are stored in all together. Okay, all the values for column two are in all together. If you want to read only the name and the salary kind of stuff, okay, in here, name, age, or kind of stuff, you don't need to read this entire thing. So, for example, let's say get the average of the ages, right? In here, what you have to do is you have to read one by one and filter out this one and get the average. But in here, what will happen is you need to read only this column, right? So then you can get the average. So that's pretty much faster, right? That's what column data store databases do, right? So okay, so the second major benefit of the kind of stuff is kind of because all the values are columns are in the same type. So all the integers and all the strings and all dates, the compression algorithms can dramatically higher ratios than the mixed type node ratios, right? So that's a kind of one uh, benefit of the column store database as well. So you can in here it say how it works, right? The data physically grouped by column instead of, and it enable the better compression and value faster reads, what I said, right? So when core is access only 2 3 columns, the in of 100 column table, the column store reads only those column, right? So I have it 90%. Yeah, that's correct, because in the row stores it must read the entire rows, even it's not fields are not needed, right? So that's pretty much faster. And yeah, this is advantages and some use cases as well. So actually efficient reads, so we talk about that one, right? So efficient reads in analytical kind of queries are pretty much an advantage, right? So the analytical team patterns actually aggregate many records, but only few columns, right? So it's exactly what column is to optimize, right? So kind of if we take sum or average or maximum group by, so this is a kind of a dramatically fast on the column stores, right? So that means better compression. Other one is better compression, right? Similar data types store all together. All integers are in a one block, right? All strings are in a one block. This is homogeneity enables to much higher compression ratios, right? So then, for example, when you are storing 100 petabytes of historical data, 10:1 compression ratio have 70 saves 90% of storage, because the at the cloud storage it might cost, no, so it's help to saving over the much more cost in per month as well, right? Because the better compression reduce the cost storage costs as well, right? So then other one is high performance one, so uh, we already talk about this one. And so if this is efficient in batch inserts as well, right? So when multiple roles insert at the same time, it updates on each column, right? So block can be batched together. So reducing the IO overhead as well. Okay. So uh, okay, so actually there's a place that the column stores are not appropriate, right? For example, let's say the transaction processing where you need to read and write all the feeds individual records frequently, the application requires complex across all the rows, right? So this workload is very high, and it should be maintain the individual records now. If you need to read and write all the individual records frequency, so the column store databases are not appropriate, right? So this is a kind of a visual store, okay, kind of a visual comparison of the row store and the column store one. And actually row store, actually it store the row is store at the entire rows together on a disk, right? So then okay, so for example, let's say if we take block one, this is block one of the disk. The it has one Alice kind of stuff, right? If we take the block two, in here actually uh you know stored ID to block this record, right? So each row is stored together. Okay. So actually this is good for OLTP system. The transaction system is insert, update, delete operation kind of stuff, right? So and in the column store, the disk level actually it's a if we take on this one, okay, just okay, so if we take this one, actually this is block ID is on block one, right? So name is in another block, age is on another block, right? This is how it is stored. Okay, so each column is stored separately, and so in row store it's row by row, and here it's column by column, right? So it's entire row together in here and same column in together, and this reads all the it reads full row, and here it reads only the column it needed, right? So then compression is low in here, but it's compression in high in here because it's similar values are together, right? So yeah, that's the this is the query type, and this is select age from. So we need to read full 4 columns, but it's need to only 4 columns only. And this is exactly read what it need, select all from, something like that, and read and assemble 4 separate blocks in here. And this is really slow, right? So it rows entirely, and this is kind of very fast because reads only one block, right? So now let's move to the actually uh, mm, okay, the kind of this is key value store, right? So if we okay, so key value store. Okay, now if you move to the key value store, so the definition is simplest, not SQL data model. The data is stored at actually key and value. I think uh, in the one good example is Redis, right? So you store data as key and value, right? Each key is actually unique and is used to directly access its associated value, right? So what happened in here is actually uh, yeah, it's to like kind of a dictionary map, right? So for example, key is a kind of a unique ID and value is a kind of a data. Okay, so it can only three very important operations. So actually, get key, set key, and delete key, right? So these are the operations: retype a value, write a updated value, and delete and exist, right? So there's a limitations as well because no joins, filtration, sorting, complex aggregate queries, right? So these are the key limitations as well, and this is very simple, right? Then exactly what it happened in here is actually um, the internal uses kind of a hash table, right? It's a one-time lookup. So hash function may maps any key to a specific bucket, and where the values are stored in here, right? So it's something like here, right? So this is the key. It has a hash function and is stored in here, right? The hash buckets. Okay, so sometimes the value in the key value store can be more complex than a simple string because the Redis also, for example, Redis, right? So Redis supports multiple structures as a value, kind of leads, sets of sorted lists, hash maps, right? So this makes a kind of a versatile far beyond kind of simple caching, right? So I used in the industry actually I one at a time I use the Redis as a caching mechanism. So for example, there's a limitations as well, right? So I'll tell you that one. So then so this is if you go to the architecture and distribution. right? So it's partitioning. So data is distributed across the nodes using the consistent hashing, right? So consistent hashing is kind of a deep concept, right? I will tell you what it happened. I have a good example for you. Let me think. Okay, so it's something like this, right? So imagine a clock. Okay, so clock is 0 to 12 now. Then it you know back to 0, right? It's a clockwise, right? So for example, let's say that the put servers on a kind of a clock, right? So for example, let's say if we choose server A into number 2, then server B into number 6, then server C into number 10, right? So we think that we are using the consistent hashing, and it's a kind of a clock. Clock is 0 to 12, again back to 0, right? So kind of is stuff, right? So that means server is kind of a number 2, then um 6 into kind of server B, and server C is kind of a number 10, right? So if user use put the data on the clock, and if user is using number 4 on the clock, and what will happen is it sets to server B, because user 1 is if user use number 4, right? That means put data using the key. If it's number 4, then what will happen is it move clockwise until you hit the server. That means um, user if user get number 4, the next number is what? It's number 6, right? So number 6 means server B. Okay. If another user get number 9, the next server is number 10, right? So number 10 means server C, right? Likewise, when the data is coming, it is the data is distributed across nodes, right? The hash of the key determines which nodes to stay. Okay, it enables kind of a horizontal scaling as well, right? So this is a kind of consistent hashing. So you can refer it actually. You can just use a kind of a AI tool and ask what is consistent hashing. So this is a kind of in-depth kind of a concept, and I just give you a kind of a sound idea, right? So then, yeah. So then the other thing is actually, as I know, it uses kind of a value to 0 to 2 to the power 1 to 8, right? So that kind of uh, space is conceptualized for the ring, right? So each node is assigned kind of a portion of the ring. For example, I say that when you get the clock, so number 2 is server 1, number 4 is server C, kind of stuff. So in the real example, for the also the each node is the design on a portion on the ring, right? So then a key is hashed to actually hashed in position the ring and store it the first node from the clockwise, right? So I tell you that if user get number 3, the next node is what? Next node is at the number 6, it's server B. So then it will go to the next node, number 6, right? If user get number 7, so it pass the number 6th node, no? 6th number, no? So that means it go to the other server. Likewise, in the clockwise, it takes that positions, right? That helps to horizontal scale. So the other factor is replication, right? So replication is actually there's a typically tree production in the cluster. That means every piece of data exist in the three different of nodes, and if one node fails, so the other two is still served the data, right? So if all three happen to be in the same data center, the data center lost power, you could have a problem. But but in the production is stuff, the replication also in the different availability zones as well, right? So the other factor of the distributed architecture is eventually consistency, like Amazon Dynamo, the replicas are eventually synchronized, right? So different node maybe temporarily return different value for some same key, but it's a kind of a millisecond, right? So this is a kind of a performing stuff, the lookup one, and the horizontally scaling, because we use the consistent hashing and in-memory support, right? So Redis is kind of a in memory kind of a stuff. We can use kind of a memory, right? So there's a concept called hybrid caching, right? That means caching in memory, then mem then as well as in the Redis as well, the distributed caching, right? So it's pretty much extremely faster, because the constant time we are using to read it, right? So then the other thing is actually what is it? Mm, okay, so the high scalability actually, because the scaling across the clusters is straightforward, and adding nodes is increase the capacity to the linearly, and it's a simple design actually. So it's easy to implement, operate, and maintain, and high read and write throughput, right? So it handled hundreds of thousands of operations per second. Yes, that is correct. I experienced that one as well. And I use Redis at a once at a application. So ideal for caching and real-time tracking. Yes, because in the, normally in the airline domain kind of stuff, we are using Redis, right? So it's a kind of a real event-time tracking as well. So in the Azure side, Redis is kind of persistent Redis and not a persistent one, right? So that means Redis wipe the data actually after kind of a 1 week, because it's a cash in. So we can get the permanent Redis asset, but it's too much cost. So the limitations are kind of not for data relationships, right? So relationship be logic must handle in the application code, and complex analytic queries are impossible, right? Not a replacement for data, and the application manage all the relationship and checks and indexes manual, right? So other limitation is kind of a no range of querying, filtering, sorting like stuff, right? So yeah, these are the limitations, right? So actually there's a these are kinds of visualized one. So for example, let's say on the left we have keys, right? User has C1001 key, session has ABC key, product and card, right? So what happen is, and the hash function take each key and then produce the number of in a fixed range, right? Because it's a hash function, no? So the this that help it to distribute the keys uniformly on this range, right? So there are 6 bucket. So this hash function is kind of help to uniformly distributed, right? So no single bucket gets actually overload, right? So the same key always produce at the bucket number, something like that, right? So you can always find your data that you store, right? Then so on the right, we have buckets, right? So the physical storage location, right? So bucket 01, then this is for user 0 1101, right? So bucket kind of other kind of stuff like that. Then there are that means it is, I want to say that it is uniformly distributed, right? So not one single bucket get overloaded, right? So this is the normal kind of expected in the hash table as well. And or above 70% of the bucket are occupied, right? So that means two-way hashing to the same bucket, so remaining rare, and it keeps lookup close time, right? So that's the deal. And for example, I will tell you. So yes, in when you go to the industrial level, you can use the Redis as a cache. So what I implemented there is actually I implemented a kind of a hybrid cache. Now we have inbuilt libraries for that. So but in that time I use kind of a hybrid cache. What does it mean is, first, let's say we need a kind of a flight detail of a flight number 123. So if we are recurrently use kind of a API stuff, there are a couple of things that can be happen, right? So there are the output in the IO operation can be happen. So if there are more IO operations, it can be kind of a memory leak stuff as well. The more memory is using because of the IO operation, right? So for that one as a solution, we can add a caching layer. So that in the first time, I use only Redis, the direct distributed cache, right? So think about that. I use a kind of a JSON around let's say 2000 line. It's a big JSON, right? So it contains all the flight details in a one big JSON. What I need to do is I just cache in there, and first I call the API, then um, no, sorry, first I call the kind of caching. I search for the I put the flight ID as a key, right, with the date. So that means let's say the flight AC123 at 2016 10th of June, right? Something like that. I use a kind of a combined key. Then I put a value that large JSON um, in the caching, right? So for the very first time, I just search in the Redis. So okay, there's no for the very first time there's no record, no. So then I go to the API call. Then okay, then I got the API response. I cache it and send the response back to user, right? So that's a kind of a caching mechanism. So what happened is actually it then for the next time it it does not call the API, right? It only search in the memory, because in the very first time we stored the um, response inside the cache, no. So now we have the cache in the response, then we got that response and send it. So there's no API call, right? That's the usage of caching, and it can increase the response time as well. Okay, the low latency. So then the what happen is when I go to the production, so for example, there are a lot more requests for the cache, right? So there is a kind of a crash in the cache, right? So when the kind of the last day I talk about the peak level and off peak level, right? So in the peak level of the flight arriving, so there's a crash in the cache, right? Every time the cache there's a the cache is went down. Okay, so when I deal with the kind of dynamic stuff, it say that there's high peak of requests are coming to the caching, right? So then what I did is I increased the kind of nodes and the size of the one kind of a horizontal, right? So then there's a limitation on the cache on the Azure side. Azure, there's a the service the product called Azure Redis, right? So on the Azure Redis, there's a kind of limitation, right? So kind of let's say over 9 GB one we cannot furtherly extend, because either we need to make another cache, right? So that's not a good. So so in that case, so the 9 GB kind of stuff is pricing cost is kind of 9,000 USD per month. Okay, that's the cost also increased because of that issue. In the peak time, there's a more load, and because of that load, um, you know, it's every time it's the system is going down because the crash is going down, right? So what I did is I just try to find what's the root cause there. Okay, there's a limitation. That's why I'm going to tell that, right? So for example, if you are using kind of a large JSON, so it's pretty much large, right? It's not a kind of small. So it's kind of 2,000 of lines, right? So when you think about the caching, we have to deal with a kind of a not much complex schema like that, right? So other thing is we have to think about the rate of the accessing that large object, right? So if it's a kind of so I did kind of a experiment to see what's the root cause there. What I did, I send the kind of let's say 400 RPS load test for the cache, and for a kind of a small structure, kind of let's say 100 or 200 lines of code, is the cache is well performed under kind of a small size of the cache as well, right? So there's a limitation. So it's in a kind of a practical way. We have to design that the more large objects are cannot be put into cache, right, and access it, right? So the other thing is rate of access in that one. So there's a so now there's a problem, right? So I cannot, chunk the response from the API and store in the cache, because in the flight detail there are a lot more details. All the things are should be in together. And then what happened is I added another middle layer between the application and the caching layer, right? So it's a kind of a in-memory one. So in-memory databases. So then what happened is system in the very first time, system will go to the API, then cache in the caching the distributed Redis caching, then it will set the value in the in-memory as well, right? So then it's tend to be kind of a very fast one, and we can use kind of a caching stuff there, and there's no nothing can be happen, right? So then in the Redis stuff, we can use this time to live as well. For example, if we insert the data, so if we want to keep it kind of for 5 minutes, okay, when we insert the data, we can put that property as well, the time to live, TTL one as well, right? So yeah, that's a kind of experience that I want to share with the key values too. That means the Redis stuff as well. So then yeah, let's move to the kind of document distro. So I will explain the concepts behind this one, and you will be having kind of a practical scenario in the not next week. So it's in the 18th of April. So we'll be get a kind of a um, holiday for next week, right? So then this is document distro, and you actually Documentist is a kind of a most accessible type of nowadays SQL database application for developers, right? So because it can be say a kind of a JSON replicants, and maps directly to the object in your application code, right? So typically, actually, there are minimal mismatch between uh, your data and your database, right? So for example, in the MongoDB, it's organized into collections, right? So that means containing logs and kind of rows, right? So, but document is not a kind of a FISI schema row. It's in a kind of a JSON object where the field makes sense for a particular record, right? Two documents in the same collection have completely different fields, okay? So, but you can keep in there. For example, consider the e-commerce platform one, right? So for e-commerce platform, let's say there are different products, right? Like laptop, okay, then t-shirt, right, kind of stuff, right, the books or stuff, right? So for example, for a laptop you have different fields, right? So the document would include what, the processor, RAM, uh, operating system, battery, right? Likewise, right, the t-shirt, it includes the size, material, colors, instruction for the washing and kind of stuff, right? So, but the booking a document, sorry, a book document, so the author, publisher, and stuff, right? So, in a relational database, what happen is you would need either more columns with for every product, right? It's very complex, right? But in a MongoDB, it's simply just a product, right? It's just a product. The product is kind of let's say this is the kind of style, its product, and then it has different kind of stuff, right? So it's a kind of flexible architecture there. So then so that's a call a kind of a how data organized. So it's a kind of a columns similar to data tables and contain documents, right? So similar rows but flexible. Each document is kind of self-contained JSON objects, and supported database actually supported data types kind of structured, semi-structured, and unstructured data within the same collection. And yes, document can be nested, right? So and these are the usefulness for this term. And so this the document can be embedded in subdocuments, right? Like this, right? So the node ID the items it has another different, right? So SKU and quantity. Likewise, no join operation needed, so the data lives together, right? So that's a kind of example and definition for MongoDB, and this is a kind of a schema flexibility, right? So if you say in the write on SQL, we talk about this one, right? So then schema on write, so then the Mongo and schema on read MongoDB, and you can see this one, right? So then you can see the schema definition required. Uh, that means upfront, and no new fields can be added to any document at the time without migration. But in here, scale on, you need to alter table and migrate it, right? So this is the way that and so in that case, sometimes the application can be cracked, right? So but the in the reading time, the application can edit this kind of new fields. Okay, so this is called schema flexibility, right? So the the risk of schema flexibility is kind of data quality over time, right? So when there is no enforced schema, so different application version may store data in a kind of a uh, inconsistent way, right? So over the years, the MongoData DB collection can be accumulate dozens of kind of different shapes of data and kind of stuff, right? So and yeah, so these are the kind of schema flexibility that we need to talk about. And again, we have kind of the document store internal query capabilities, right? So if you talk about the document store kind of MongoDB, so understanding the kind of internal patterns that make you to design a better decisions, right? So MongoDB is a kind of a document base. It can be a kind of uh, it is to documents in the basin, right? That means binary JSON, right? So a binary encoded format. It's a kind of fast on serialization, deserialization, right? So that explain the JSON to support additional data site types. Okay. So then a document as a JSON can be loaded directly into memory and at a native object. So the like Python dictionary, Java maps, and no transformation is required, right? So that's why its serialization and deserialization is pretty much fast than the plain test, right? So that this is correct. Actually, I also experienced that some of the, when you so when you build an application, so you need to make sure that it handles the production loads, right? So sometime you will see there's a kind of a memory leaks, right? So what you have to do in that case, you need to do a kind of a profiling stuff. So profiling means, so we run the application, then there is a kind of a profiling tools. So I am using kind of a Visual Studio. So in the Visual Studios, we have kind of profiling stuff. What we can do is we can run the application and send the request to uh, the application. And when the runtime matrices are uh, showed in that kind of framework, the profiling frameworks, right? So sometime when we send the request over and over again, we seen that memory is getting um you know increasing by request, right? So there is a kind of a garbage collection there. It should collect all the unnecessary objects in the memory and just lose it. But sometimes it's not working as expected, right? That's called memory leak. So in that case, I used to find the serialization is a kind of a stuff that we need to do more efficient. We need to more handle efficiently. Otherwise, it can be a problem for the high load of programs, application running on in a kind of a production environment, right? So Indexing is it's a kind of a document support indexing on any field, and then including nested fields and arrays, and indexing available fast queries, without full collections of scan, right? This indexing one. So then the other thing is actually replication and sharing, right? The replication set you high availability to automatic failover, and shading describe the data across all the nodes and shade for horizontal scaling, right? So this is a query capability. So rich query supports, unlike key value stuff, the document supports complex query, right? It can actually filter fields by values and search nested data, sort result and stuff, right? So this is the aggregation pipeline. So the Mongo aggregation pipeline is multi-stage data transformation, like filtering, grouping, then projecting output, right? Similar to the SQL group by and joins, right? So it can have kind of stuff as well. So this is text search, kind of fully text search index on, and geospatial queries, also location based lookups. We can use that one as well, right? So so typically in the MongoDB replicas three nodes, so one primary and two secondary nodes, and our write goes to primary node. So then which replicate into secondary one asynchronously, right? So if primary fails, the secondary elect a new primary as automatically, and that provides a kind of a high availability on data, no data loss, and committed for writes, right? So then actually so let's move to the other one. It's talk about the document is to advantages and limitations, right? So actually, because like all NoSQL databases, they are excellent for some use cases and problematic for others, right? So kind of using them, if you're using them wisely, you can have kind of a very good solution, right? So the advantages are actually compiling for the right workloads. That means the flexible schema accelerate the development, and accommodate the variety of data structure without overheading schema migrations, right? So add a field to document and without affecting the others in the same collection, right? So for fast development cycle, particularly the valuable for startups and agile teams where requirement change frequently, right? So that I'm also in a kind of a startup, and so every time there's a kind of a development cycle, right? Every time they ask for the requirements are changes frequently, right? So in that case, adding a kind of filter document, without others in the same collection, that would be a flexible schema advantage, right? Then fast development as well, and then handle complex and extra data. I saw that naturally the model in the real world objects, um, you know, give me a minute. In the real world objects, actually, with the sub object of arrays, uh, it's a more actually combining and relationship data, right? So eliminates complex on join operation that needed in the relational database as well. So that handles a kind of complex scenario very smoothly, right? So then other thing is horizontal scalability, right? So for example, big build for big data workloads, and scaled out across clusters using shading, and handle millions of documents with distributed read-write performance, right? So yeah, by the way, we have limitations as well, right? So no native joins operator like scale, but the related must be embedded for lookup and separately by the application, right? So not ideal for ACID transactions, right? So multi document transactions are supported in MongoDB, but it kind of performance trade-off, right? So then yeah, data duplication. So sometimes the denormalization means same data may exist in the multiple document, right? So update must be applied on all copies, and it should be created maintenance as well, right? So it's a can be overhead as well. So these are the key limitation. I just explain it quickly because in the next week I do a kind of a practical scenario based on this one, the document is the one. So you can have a kind of a check on the Redis stuff. There's a UI call for the. I mean, I'm talking about the key value store, right? For the key value store, you should just looking in that because the most company using that one, and in the kind of interview stuff, you will be valuable to say that okay, I have some experience in the Redis kind of stuff like as well. So if you want to see the kind of uh, the key value store value in a kind of a UI stuff, you can use there's a application called another Redis desktop. So you can use that one and you can see how it store data and key value pair kind of stuff as well. So okay, so we deal with the document store as well. This is a kind of NoSQL database. Again, the column store database and how it work and kind of a Cassandra family example as well. So this is a key value document stores and you can see in here and then so these are some example for you. So the other thing is actually we need to know about is the database landscape, right? So it's in the right tool. So we have covered, more database types, right? So now let me give you a kind of a decision framework to choose between them, right? So you will be justify your database choices, the technical thing, right? So this is a comparison table. Is just show 5 key decision on dimension on the data model, schema, scaling, consistency, and best for, right? So you can see in the relation data model table with rows and column. This is column separated and key value pairs and this is document is so JSON or BASIN documents, right? So this is schema on right, semi-flexible, and no schema in it is highly flexible, and this is for document, right? So this is vertical plus horizontal is complexity because the actually the cloud database it handles smoothly, but it's much more complexity because of the statefulness kind of stateless and statefulness kind of stuff, right? So this is horizontally scaling, shading, and easy to horizontal for the noise scale on, and this is also shading, right? So these are the consistency strong acid principle follow and is strong for columns and this is distributed database and is configurable, right? So these are the some base cases that suit for each and every document databases. Okay, so and so again if you need some high write throughput, actually the cache frequency access data or it can be session state the key value is to use, right? So then if your data is kind of document oriented one, it's basically you should do MongoDB, right? So kind of product catalogs, kind of user profile stuff, right? So then okay, so this is a column store kind of detailed one. So data model, the query language is scaling. The same thing I added in here as well. And then the this is for kind of document store. So the same thing I summarized and added in here, right? You can see, you can go through this slide if you want. Kind of quick tips there. And this is key value store, the query language, and this is based for joins kind of stuff. And this is for the graph database, Neo4j, and kind of stuff, right? So, and finally, this is for the relational database. Okay, so actually, at last part of the lecture, I kind of did it kind of speed way because I went through each and every concept deeply. And the last slide, actually, last 6, 7 slide, basically it contains the summarization of the database types that we talk about in the noise scale. So then these are the key takes values, right? So actually, if you talk about the key takes value, the first one is kind of acid versus base, right? So it's a question which state of fits your problem, right? So acid gives you kind of correctness and the cost is scalability, and it's a strong acid guarantees ideal for transaction, right? But the base give you kind of scalability at cost for immediate consistency. Okay, so kind of financial transaction you use acid, kind of social feeds or something like that you give base, right? Both are valid in engineering, but the choice is the apply to a right problem, right? So the other thing is cap theorem. So it's governed in the constraint of the old distributed database design. And when you choose a database for the distributed design, you choose your cache position, CA for single server system, so then CP for the consistency, non-negotiable during failures, then AP for most availability is the most important than immediate consistency. Like, so you must know which position of your use case requires before you choose the database, right? So then other thing is no scale, not only scale, right? So it's a kind of a toolkit actually, not a replacement. So the database landscape include the relational database, column stores, key value stores, and graph database. But you can see in each optimize for you know a specific data model and access the patterns, right? So then the best system use multiple database types together and each workload handle the base, right? So we talk about the column database, document, key value, or graph. It based on the problem, right? So fourth one is actually choose the right tool. So we need to think about the access patterns, not just the data model. And we want to ask kind of how data is accessed and by a only single key or any field of is that one, what consistency required, then immediate or eventual, or kind of what's read write ratio needs. It's a kind of a write heavy or read heavy. So that kind of problems give you to choose the right skill, right? So yeah, so this is the kind of key takeaways of the um, you know this lecture. And so let's see to do kind of a hands-on experience as well. And so finally there is a kind of a link there. So let me open it. Link. If you open it there, you can see the database ranking, right? So that's why I put in here. Okay, so actually there's, if you go to that link, so you can see DB engine rankings, right? So in the April 2026, the number one is Oracle, number two is MySQL, ranking number three is Microsoft SQL Server, and number four is kind of PostgreSQL. Number 50 is MongoDB. We talk about that one. Then number six is Snowflake, Databricks, Redis, kind of stuff, right? The 10th one is Apache Cassandra. So with that one, you can see the trending chart of the databases and stuff, right? So that's the end of the lecture, and we talk about the much more deep concepts about the analytics and discovery patterns and why that infrastructure needs such kind of heavy analytics performing problems. Then we talk about the acid properties, then base properties, then cap theory, and then we move forward smoothly to the NoSQL one. We talk about the NoSQL database types stuff, and I talk about kind of Redis stuff as well. And then actually you can uh, try out the Redis uh, yourself, right? So because it's number 7th ranking database, that means most of the company use that one. So then that kind of stuff you got this lecture. So yeah, let's meet on 18th of April, right? So yeah, 18th of April, and I would like to say that there's a presentation, right? Group presentation. Again, I will tomorrow I will put the group number, and overall in here actually half of the students are not in here, so tell them to I mean there's a kind of a group presentation, and so if you are not coming to that one, I will not give marks. And actually what you have to do is I will put a kind of a research paper for the foundation of the technologies stuff there. I am not expecting kind of a much more deep level. So what you have to do is you have to read it and get the idea, and you have to present it to me, right? To the team actually, to the to the students in here. And it's a 5 minutes for each student. All together, I told you it's 30 minutes. And at 11:30, let's start that one presentation, and I'll put the group number and the paper for you in the WhatsApp group. Then you have 2 weeks, so you can ready for that one. And yeah, so that's the thing that we are going to do in the 18th of, starting from the 18th of April. Let's move forward, and then let's see how we tackle the other groups as well at the end of this lecture. Okay, so that's the end for today, and thank you for coming. And again, I would like to say it's a kind of a boring stuff, but just listen to the lecture again and try to get the concept. I will share these slides as well with you. So when you get it, just go through the each slides, and if you don't understand that one, so use any kind of a tool to understand what's the concept behind that one and keep it in mind. So it will, you know, help you to move forward with industry level as well, right? So that's the end for today, guys. So let's meet on the other day, okay? And I wish you happy new year as well. So we are meeting right after the new year, right? Okay, guys. Hello. Hello, guys. Can you hear me?
Yes, sir.
Okay. All good, right? Okay, then bye, guys. See you next time.
Okay, thank you, sir.